Okay, great. Slideshow from the current slide. Turn on the laser pointer. Just a minute. Yeah. So, good evening, all of you. Welcome again for joining for this live problem solving session number 10 for the course Analog IC Design, which is being conducted by Professor Sankaran Anirudhan from IIT Madras. Just to introduce myself again, I am Soham Lakote, currently a 5th year PhD student at ISC Bangalore, working under Professor Gaurav Banerjee in the area of vital signs monitoring using the FMCW radars, which is a subpart of analog and RF circuits. So again, the session organization will be same. We will see if we can take a break today for 4 or 5 minutes, because in the end I would like to cover one design problem so that most of the concepts that has been taught in this week it will become completely clear. Just for the formality sake, all the lectures are being uploaded in this YouTube channel. You will be able to find the link for the lecture notes in the description section of the YouTube video, and I hope all of you are able to access them. And so this will be the organization of this session. So first we will have a quick look at the concept of differential and common mode half circuits, which will actually help us to get the output response of the differential, any differential symmetric circuit with respect to the common excitation or the differential excitation. Then based on that we will solve at least 3 or 4 different problems, and then we will move on to the concept of input and output common mode range. We will also take one example so that we will get some feel for the numbers, and at the end we will solve one 5-stage OTA design problem which was posted by Professor Iman Mondal from IIT Kanpur on the LinkedIn. So we will try to see how we can solve that particular problem. We will not be able to solve the entire problem, but at least we can solve at least 60-70% of the problem, and rest of the stuff I can give you as a homework. So now let me just start with this. Let me just turn on my pen. Yeah, so what is this concept of differential and common mode half circuit? So I hope all of you are at least familiar with the differential circuits. At least you have watched the lectures. So these differential circuits are nothing but you have some load, symmetric load. What do I mean by symmetric load? If Z out is present on the right side, this will also be present on the left side. Correct? Then you have transistor, the differential pair, correct? M1 and M2. Then you may have some circuit over here as well. This I am denoting as ZD, that is the degeneration load that is present at the source of the MOSFET. And then here you will have a tail current source which is doing its job to bias these transistors. Correct? What you are applying at the input. So basically you have two things. You have a differential plus common mode excitation, and since you are applying VD over here, you are applying minus VD at this particular point, and the common mode signal remains same for both the inputs. Correct? So this is the basic structure of any differential pair that you will see. Any differential pair can be categorized into this particular structure. You just have to identify Z out and Z degeneration. So the most of the problems that you will be able to see in the Razavi's book or any analog circuits book, they can be categorized into this kind of general structure. So the common thing that they will ask you is to find out differential gain of the circuit, then common mode gain of the circuit, and hence they will also ask you to find out the CMRR. That is the common mode rejection ratio. Ideally, what is the job of the differential circuit? First of all, why are we even studying the differential circuits if we have the common source amplifier? Correct? So now let me just quickly clear that particular part. Remember, you have a huge chip area. Correct? You may be designing the entire radar transceiver or communication transceiver, which may be very, very complex. Correct? This is just one of the circuit that is present at the baseband part of the transceiver. Correct? Now the problem is this particular thing that you are seeing over here. Now any noise can get coupled at this particular net, and from where the noise can get coupled, remember you have RF transceivers, right? RF transceivers will usually have the inductors. Correct? They will usually have the inductors. Now just tell me what will happen if I pass a current through this inductor. What is going to happen? AC current, I am talking about AC current. What is going to happen? What is going to get generated around the inductor if I pass a AC current through this inductor? A time varying current basically. Guys, any answers?
Some phase and voltage.
Phase and voltage. Okay, but what is the basic job of the inductor? How does the inductor stores the
Magnetic
energy?
field.
Yes, very good. So there will be magnetic field that will be generated. And what is the chip area? So chip area can be something like, if you talk about the maybe two, if you take two rectangular dies like this can be something like 3 mm cross 1.5 mm. Correct. So the purpose of telling you is this is the this is what you are passing is time varying current. This will generate a time varying magnetic field. Now what is this? So this is another metal layer, maybe metal 1 or metal 2. Correct. Now the purpose of telling you this is there is a time varying magnetic field that is getting generated over here, and there is a conductor that I have just placed over here. Correct. So now what happens? Let's say if this is a conductor that I am placing, correct, and there is a time varying magnetic field that is going on. Correct. So this conductor is sitting in a time varying magnetic field. Correct. And you know from your class 12 physics, right? Your class 12 physics, right? There will be a voltage that will be generated at this particular net. Now the thing is, I don't want this is a noise, this is interference, I don't want to amplify it. Correct. So what is the best way to reject this interference? So the best way is to replicate this circuit, take the input as the differentials, so that same interference, same noise, the voltage that is getting generated because of the time varying magnetic field, correct, the same voltage will be present at both these inputs. Correct. And when I take the difference, correct, if I write the output, if somehow I get the output which is, let's say, proportional to A is the constant, as Vin plus minus of Vin minus, correct, then this interference that I am getting, that is generated within my own chip, right, it will get rejected. Correct. So that is why we are working with the differential circuits. And if you look of the papers that I had shown you in the first lecture, correct, just go back to these papers and just look at the baseband circuits. You will see the complete differential chain, right? Only at the end where you are gonna connect the pad, right, that is the baseband output, you will see a single ended thing. But rest of the processing, maybe if you take at the RF end or the baseband end, most of it will happen through the differential circuits only. Correct. This is the importance of the differential circuits. So now how are we going to work with this? So basically, let me just change the color of the pen. The reason why we are studying this is to check if I place a common source amplifier, if I place a differential circuit which in a very noisy environment, correct, how much it is able to reject the interference and how much it is able to amplify the signal, which is the original signal that I actually wanted to amplify. So the way to work with this circuit is to always draw a line of symmetry. Correct. Always draw a line of symmetry. And now two things we have to do. First of all, what should we do for finding the differential gain? Correct. So for differential gain, we have to draw something called as a differential half circuit. And similarly, for finding out the common mode gain, you have to draw a common mode half circuit. Now the difference between these two is along the line of symmetry. Correct. Along the line of symmetry, whatever you will get, correct, for the differential half circuits, you are just gonna connect it to the ground. Correct. You are just gonna connect it to the ground. So what do I mean? So if you see some MOSFETs like this, correct, if you see some MOSFETs and these are getting biased with some common bias voltage, correct, so you have to connect this to the ground. Even if the bias voltage is not present, you have to short this node to the ground for calculating the differential gain. That is, first we will draw the differential half circuit. While drawing the differential half circuit, you are gonna short everything that is gonna come along this line of symmetry. Correct. And then we are gonna just work with one part of the circuit, not everything. Correct. And then from the traditional methods, whatever we have seen, right, the effective GM and the effective output impedance, from these methods we are going to calculate the differential gain of the circuit. Now similarly, for drawing the common mode half circuit, what you have to do, first of all, you have to make sure that the circuit is completely symmetric. What do I mean? This I tail that you are seeing over here, this is usually implemented by the MOSFET. So there can be some tail resistance that will be present over here. Correct. Now this tail resistance, now what I have to do, since I am dividing the circuit in two halves, correct, I have to make it symmetric. Correct. So now I have to take two resistors and their equivalent resistance should be R tail. So can anyone tell me what will be the value of each of these resistors if I connect them in parallel?
Twice of RT.
Yes, very good. So it will be twice of RT. So this is what I have to do. Correct? Why does it not matter for the calculating the differential gain? Because remember, this point is gonna get short circuited to the ground for drawing the differential half circuits. The other, so that means the upper end of this R tail is grounded. Even the lower end of this resistor is grounded. So the R tail does not matter when you are actually drawing the differential half circuits. For the common mode half circuits, this definitely matters. Correct? And you know now that this R tail is one of the reasons why the common mode rejection ratio of the circuit is not infinite, while you will get the finite common mode rejection ratio. Correct? So this is the procedure that we are gonna apply now, and now we will be solving few problems. Correct? So that this concept becomes extremely crystal clear to all of us. So now let me just move on with the problems. So let me just change the color of the pen. Maybe red will do. Correct. So now what we'll do is we will first attack this particular problem. So now, by the way, this I have not mentioned the reference over here. So this I have taken from the like me. So there was a past TA from IIT Kanpur. His name was Mayank Anupam. So I have taken this problem from his YouTube channel. Okay. So now let's look at this particular problem. So now first what I have to do, I have to solve the problem number A. And now I have to do what? I have to first draw a line of symmetry. Correct? This is what I have drawn over here. Now first I have to do what? Differential half circuit I have to draw. Correct? So now let's try to draw the differential half circuit. So now if you look, this VDD will be grounded. Correct? Then what do I have? This is V bias, so this already would have been short circuited to the ground for doing the small signal AC analysis. Then I have this transistor M3 over here, correct? Even its gate is grounded over here. Then I have M1, correct? Then I have RX, and since this is also shorted along the line of symmetry, this will be connected to the ground. This is where I am applying the input, correct? And I am taking the output where? I will be taking the output here, correct? Because this is a differential, because this circuit is exactly symmetrical, right? So this is where I will be taking the output. Correct. So now, can anyone tell me what will be the GM of this circuit? The aim is now to find V out by V in, and we will always follow our traditional method to calculate what? To calculate the GM first, then calculate the R out, then multiply 2 to get the AV. Correct. This is the method that we'll be following. So let's do the first step. What is the GM of this circuit? Can anyone tell me what is the GM of this circuit?
GM divided by 1 plus GM1 RX.
Yes, very good. GM1 upon 1 plus GM1 times Rx. Correct. So the GM is already done, and from where did we get this formula? We have already done it a lot of times in the last 2 lectures, right? So we have solved this, and we have also seen a lot of shortcut formulas which are gonna help us to solve this kind of numericals. Correct. So if somebody is joining this session for the first time, then I will refer you to please refer to the past 2 lectures. You will see from where this is coming. So now GM we got. Now the next step is to find out the R out of this circuit. Correct? So now what is the impedance looking on the upside over here? Z up. What is the impedance?
R0.
Yes, R03. Very good. And what about the Z down? Assume a finite R0 over here. Okay? R01. What will be the impedance if I look down?
GM1 R0.
Yeah, very good. Yeah. So this is approximately correct. Entire expression will be too big. So the R out total will be nothing but the parallel combination of this, correct, into GM1 RO1 times Rx. So now you have got the GM, correct? In the first part, let's say this is A, let's say this is B. So AV will be nothing but this GM1 upon 1 plus GM1 times Rx into RO3 parallel GM1 RO1 Rx. Correct. So this is a differential gain that we got. Okay, this is differential gain. Now we also have to draw common mode half circuit, just like we have drawn over here differential half circuit. So now the only difference is this I bias. Now I have to assume that there is a R tail that is present. I could have taken it ideal, but it's important to complicate a problem little bit, right? So now this is done. The way we are going to do it is we are going to split this R tail into two resistances, correct? So now that resistance I have to take into account, and for common mode half circuit along the line of symmetry, right? Whatever is there, you are going to open circuit it. Correct, you are gonna open circuit it. You are not gonna short circuit the short circuit whatever is coming along the line of symmetry. For the differential half circuit, you short circuit whatever is coming along the line of symmetry. But for what you can say the common mode half circuit, you open circuit basically whatever is there along the line of symmetry. Correct. So now let's draw the circuit, the common mode half circuit. Correct. So how will the common mode half circuit look? So first I had the VDD on the top, so that is already grounded. Correct. Then I had a transistor. Correct. The transistor M3. And remember what was connected to the gate of the transistor? It was V bias. Correct. So that V bias will be connected to the ground. Don't think that it will be open circuited because V bias was already connected over here. Correct. Now this was M3. Now we have M1. Correct. Now on the bottom, what do I have? I have this Rx resistance, correct? Rx. Then what I had done over here, there was a tail current source which I had splitted into two resistances, correct? Two parallel resistances like this, 2 times R tail, correct? And this particular node came along the line of symmetry. So I have to open circuit this particular point, and there is your Rx that is present over here, correct? So I hope you are able to imagine this stuff. So this R tail I have divided into 2 times 2 R tail, correct? So now along the line of symmetry I have to open circuit this particular point. So the total resistance that will be present at the source of M1 will be Rx, and then I have 2 R tail, and this R tail's other end is connected to the ground because this I bias other end is connected to the ground. So this will be the total thing that I will be seeing at the source of M1. Let me just write it at source of M1 for what? For common mode half circuit. Correct. So I will be drawing this 2 R tail over here. This will be grounded. This is where my input was. This is where I am taking the output at. Now tell me the GM of this circuit. What is the GM of this circuit? What will be the GM?
GM1 by 1 plus GM1 into Rx plus 2 R.
Very good, correct. 2 times R. I hope it is clear. If any doubts are there, please ask me. Now, this is very obvious because this Rx and 2 R tail are coming in series, right? Now, once this GM is clear, now let's look at the R out, correct? So, on the upside, what do I have? I have RO3, correct? So, let me just write this. So, first, let's say this is Z up. Similarly, I will be having the Z down as well, correct? The impedance looking down over here. And the Z down will be similar to what we have done in the previous case. It will be GM1 times RO1 times the whatever resistance is there at the source, Rx plus 2 RT. Correct? And this is approximately. So the total gain, the common mode gain, will be nothing but this particular complicated expression. 1 plus GM1 Rx plus 2 R tail, right, into GM1 RO1 Rx plus 2 R tail. Correct? Now the only question that I want to ask you is, what do you think which GM was higher? So this particular GM that you are seeing over here, or this particular GM that you are seeing over here? This is my first question. And the second question is whether this is a good news or this is a bad news. That the GM which is coming higher, like it should have came higher or it should have came lower. So what about this GM? This GM is lower or higher than the previous case?
It's lower than the previous.
It's lower than the previous case, right? And it's a good news or it's a bad news?
It's bad thing.
It's a bad news. Just think again, this is a common mode circuit, right? So any common mode signal that will be presented on these input nets, now it is seeing a heavy degeneration because of this 2R10. Correct? It is seeing a heavy degeneration, that is now the GM has degraded for the common mode excitation. But if you look at this particular GM, this is the GM of what? This is the GM for the differential inputs. So now this circuit is presenting a higher GM for the differential inputs that I want, and it is presenting a very low value of the GM for the common mode signal, just like the voltage that was induced by this time varying magnetic field that I have shown over here. This particular voltage I was talking about, correct? So any signal that is a common mode signal that is present at this net, so for that the circuit is actually presenting a lesser value of GM. So it's a good news or bad news now?
Yeah, it is good news.
Yeah, it is good news, right? So the circuit is doing amazing job. You can see that at this particular node, right? This is the tail current source over here. There will be some capacitance also that will be presented. Correct? Now at extremely high frequencies, which one of this will dominate, the RL or CP? Which one of this will dominate? The impedance of CP is nothing but 1 upon SCP. I'm talking about extremely high frequencies.
So it will short circuit after.
Yes, exactly. It will short circuit, and the problem that is going to happen is there will not be any degeneration that will be present now. Correct? So this 2RL is basically short circuited to the ground. Correct? So this 2RL factor will not be present, and whatever gain, whatever GM that you are seeing over here, correct? For this particular circuit, the differential mode excitation, the same GM you will see even for the common mode signal. So now that is a bad news or that is a good news? Are you able to understand?
Bad news.
Say again.
It is bad.
Yes, it's a bad news, correct? Because your GM should be as low as possible for the common mode excitations, but this CP is completely ruining everything, correct? This CP is completely ruining everything, so this is a main culprit which will kill the CMRR, that is a common mode rejection ratio, which is nothing but the ratio of the differential gain to the common mode gain that we are seeing over here, correct? If you divide it and take the 20 log of that term, you will get the CMRR number in the dB. Correct? I hope this particular part is clear. We have already done the part number A. Now let's move on with the part number B for this circuit. Correct? So this is a part number B. Remember, this is not horizontally short circuited. The gates of M3 and M4 are not connected over here. I am just drawing the line of symmetry. Correct? Again, we have to do the same thing. We have to first draw the differential mode half circuit for this. Then we will calculate the differential gain. Then again we will draw the common mode half circuit. We will calculate the common mode gain, and we will see what we are getting. Correct? So let me just draw the. Yeah, you have some doubts?
If I'm not doing half circuit for this, so like, do I need to do a small signal analysis?
Yes.
One as V in as the input, and other is minus V in as the input.
Yes, you need to do that. You can still apply some techniques like the impedance looking down, impedance looking up. So for example, if you consider, so now there are two inputs now. One is the V in over here, correct, and another is the minus V in over here. Correct? We are doing the small signal analysis. Small signal analysis means circuit is still linear. You know that any LTI system I can apply the principle of superposition. Correct? So two inputs, what I will do, one of the inputs I will ground, and then I will calculate the output only with this particular input. Correct? This V in over here. Now for this particular transistor at the source, you can see that you have Rx, you also have a Rx over here. Correct? And then you have impedance looking at the source of the MOSFET on this particular side. Correct? So now this particular source, the transistor where input has been applied, so its source will be degenerated now. Now through that particular degeneration impedance, you can calculate, if I apply an input over here, I have a R0 looking up, correct? I have some impedance looking down. What will be my voltage at this particular point? Correct? So you can still apply some formula and the techniques, short methods that we have seen, but you need to do that. You need to literally consider V minus V and then calculate the value of Vx and Vy at this particular nodes, then subtract both of them, you will get the voltage gain of the circuit.
Okay, sir.
Yeah, good. Yeah, so that was a good point. And normally whenever the circuit is not symmetric, you generally have to do that. What do I mean? If M1 has some mismatch with respect to M2, correct, or the load that you are seeing, it has some mismatches, correct, you have to go with the traditional analysis. That is going to be little bit lengthy, but you have to do that, otherwise it's going to be very difficult. And note, we do not deliberately introduce mismatch in the differential circuits, because that is not what we want. We want this circuit to be perfectly symmetrical, so that any common mode excitation will face heavy rejection, correct. And to get that, we have to make sure that the transistors are matched. Transistors are matched as close as possible, correct. And to what do we need to do to match them closely? We need to increase the area, correct. We need to increase the product of W and L. And note, these transistors, they are not operating at the RF frequencies, correct. We are talking about the baseband circuits. So when do you need the minimum channel length that is available in the technology? You generally need them to design the RF circuits, correct. So if I give you 180 nanometer technology, it does not necessarily mean that you will choose the channel length of these MOSFETs as 180 nanometer. Generally, to make sure that you get a high enough output impedance, that is R0, correct, you get high enough output impedance and you get a good matching between M1 and M2, you should generally take 3 or 4x of L-min, that is 540 or even 720 nanometer of channel length, correct. Your FT will definitely degrade, but that does not matter over here, correct, because what you are doing is you are not trying to amplify the RF frequencies, you are just working with the baseband circuits, correct. Unless and until the frequencies, the 3 dB bandwidth requirement of your op-amp itself exceeds like 500 megahertz, maybe 1 gigahertz or something, correct, there is no point in using the minimum channel length over here, correct. So that is one more important point that I wanted to highlight, that you should take a note of while designing circuit, maybe in LT Spice or maybe in Cadence as well. Right, so now let's look at the question number B. So this was the question number B that we had. We are drawing the differential half mode circuit. Just give me a minute. Yeah. So now let me just draw the differential half. Sorry.
One doubt is there.
Yeah.
So in the previous question, that RO3, if you consider differential half circuit, then it would not be equal to 1 over GM5.
Sorry.
In the RO3 Z up, will it be 1 over GM3?
Oh, okay. So that is your doubt. Okay. So now let me just take a highlight over here. So what this person is saying is, this is the grounded. Even this is grounded, so it is acting as if the gate and source are shorted, correct. So impedance looking up will only be 1 by GM for the diode connected MOSFET. So if I look at the impedance from the source side, correct, this is the drain side of the impedance. The diode connected MOSFET would have looked something like this. It would have looked something like this. Its gain and drain would have been shorted, gate and drain, correct. Here the gate and source are shorted. So impedance will still be higher because I am looking at the drain node of the MOSFETs. So that is why it will be R0, not 1 by GM. Yeah, correct. So now I am drawing the differential half circuit for this particular problem. So on the top, what I had was VDD and grounding it. Correct. Now I had a transistor M3. Correct. I had a transistor M3 and now it is diode connected. Correct. Just look at the circuit again. This is a circuit that I have. The gate, these are the M2 and M4 of PMOSes. Correct. The gate and drain of them are shorted, so these are the diode connected devices. Correct. So now the person who was asking doubt, here your 1 upon GM concept will come. Correct. So this is M3. Then you have M1 over here. Correct. Then I have that RX, the RZ resistance was there. Correct. And since I am drawing the differential half circuit, the tail resistance, the resistance of the tail current source does not matter because it gets short circuited anyhow. This is VN and now this is V out. Correct. Now again we will do the GM. What is the GM of this circuit? Again GM1 upon 1 plus GM1 times RZ. Correct. And now the person who was asking doubt, now you tell me what will be the output impedance. If I look upside, what will be the output impedance? Yes, very good. It will be 1 over GM3. Correct. And now impedance looking down, we have already seen it is GM1 times RZ times R over. Correct. So now AV will be nothing but GM times R out, and please be very careful with the signs. Okay. I am giving the input at the gate of the MOSFET. I am taking the input at the drain of the MOSFET. You expect that there will be a 180 degree phase shift between it. Correct. So even if you ignore the signs in the final answer, your signs should be clear. Correct. This will be minus GM1 upon 1 plus GM1 times RZ into this impedance. I can approximately say is at 1 upon GM3 approximately. Right, so this will be the final answer. This is the gain, the differential mode gain of this particular circuit. Now I have to do what? I have to draw a common mode half circuit as well. Correct? Now again I will draw. I had a supply on the top. I'm grounding it. Correct? Then I had this diode-connected MOSFET M3 with me. And then I had this M1, the main transistor where I was actually applying the input. This is let's say common mode signal now, correct? Then I have a RZ, and now the tail current source resistance will also come up into the picture. 2 times R tail, correct? And now this is where I am taking the output. Again, if I write the GM will be nothing but GM1 upon 1 plus GM1 into whatever resistance is present at the source, correct? What is this resistance? RZ plus 2R tail. Again, look how beautifully the circuit is rejecting the common mode signals by heavily degenerating the circuit, correct? And if I look at the R out will be 1 by GM3, correct? In parallel with what is the impedance looking down? It will be GM1 times RZ plus 2R tail into R01. Correct? This will be approximately 1 over GM3. Correct? Now when you multiply, you can see that the GM quantity has degraded, has reduced a lot, whereas your R out it is not getting affected a lot because 1 over GM3 will dominate the output impedance, correct? So when you multiply them, of course you will expect that the voltage gain for this common mode half circuit is gonna degrade severely compared to the differential circuit that I have drawn over here, correct? And which is the desired property that we wanted, correct? So AV will be nothing but minus GM into R. So I hope that particular part is clear. Any doubts, please feel free to poke me at any point, okay? Now we'll move on with this next particular problem and we will see how we can solve this. Correct? Now can anyone tell me if I wanted to draw a line of symmetry along this particular axis and facing a problem with this particular resistor, what should I do with this resistor over here? Can I do something with this so that I can draw a half circuit? Sorry? 2R, if I do 2R and 2R, this will become 4R, right?
2R by 2 ground.
Yes, correct. So, yes, R by 2, then R by 2, correct, in series, correct? So, along the line of symmetry, this will be grounded, correct? So, this is what this person was saying, excellent. So, now what we'll be doing is, we will be doing the exact same thing. Let me just draw the circuit over here so that everybody is able to imagine this. This is RD. This is RD. Then you have R by 2. Then you have R by 2. Correct? Then you have M1 over here. Then you have M2 over here. Correct? And then I have a tail current source. But remember, we have a R tail over here. Correct? So we have to take 2 times R tail and 2 times R tail. I hope everybody is able to imagine. Now let me just change the color of the pen, maybe to black. Yep, correct. So now along this line of symmetry, I will be breaking the circuit now. Correct. I hope everybody is able to imagine it. Correct. For differential circuits, all these points that you are seeing over here, this will be grounded. Correct. And for the common mode half circuit, this will be open circuited. Correct. Do not open circuit the supply over here because I have already given the VDD over here. Correct. So you should not touch the bias voltages that were already present in the circuit. Correct. So now let me just write the differential half circuit. So I had a supply on the top, so that I am grounding. Correct. Then I have the RD that was present. Then I have R by 2 resistance. Correct. Since this is a differential half circuit, this other end will be grounded. Correct. Then on the bottom I have M1 where I am giving the input VD. Correct. And what is there? This particular thing will be short circuited. Correct. For the differential half circuit, so no degeneration is present in this particular case. Correct. So this is where I was taking the output. This is where I was taking the output. So now if you look, the GM of this circuit, the GM is exactly GM1. Because all the VGS is actually getting applied across the gate and source terminals of the MOSFET itself. Now if I look at the R out, correct? So the R out over here will be nothing but from this particular point I have one resistance R by 2 to the ground. From this particular point again I have a RD to the ground, correct? And again from this particular point I have RO to the ground, correct? So the R out will be nothing but the parallel combination of this RD parallel R by 2 parallel R naught, correct? So your gain will be nothing but minus GM1 times RD parallel R by 2 parallel R naught. So this is a differential this is a differential gain that you will be able to get if you write it using this differential half circuit method. Now it makes sense to do a common mode half circuit and see what gain we will be getting, correct? Common mode half circuit. Again I had the supply at the top which I am grounding, correct? Then I had a resistor RD, correct? Then from here I had a resistor R by 2 which is left open circuited at this particular end. Then I have a resistor, a MOSFET M1 over here, and then in the degeneration I will have 2 times R tail. Correct? We have seen this many times. This is V in and this is V out that we have. Can anyone tell me, will this R by 2 play any role in determining the output impedance or gain of this circuit?
No.
No, right? So I can completely cancel out this branch because this other end is left open circuited. So now what will be the GM of this circuit? So not small gm, the capital GM. Again GM1 divided by 1 plus GM1 times whatever impedance is present looking at the source of the MOSFET M1, correct? So this is 2 times RT. So this is a GM that I have, correct? Again you can see, compare it with the previous GM. We had a GM1 only. Over here we had GM1 upon 1 plus GM1 times 2 RTL. Remember this is a very huge quantity, correct? So if I try to approximate the GM, correct, since this quantity is very huge compared to the one, I can ignore this one over here. The GM1 will get cancelled and the GM will be what? 1 upon 2 times RTL. This RTL is very high, correct? This is the channel length modulation, the resistance that comes because of the channel length modulation for the bottom current source, correct? This will be in hundreds of kilo ohms, correct? This may be in hundreds of kilo ohms, or if like 50 or even 100 kilo ohms, correct? This is going to be a huge quantity, so the GM of the circuit is completely gone now, correct? It's because of the heavy degeneration. So again the what you can say is, for the common mode excitation the circuit is beautifully rejecting it, correct? And R out, if I look, it will be nothing but RD parallel. What is the impedance looking down? So it is nothing but GM1 times the RO1 into 2 R tail, correct? This is what you are getting. So now the voltage gain will be nothing but minus GM times R out. You can multiply, the expression will become complicated, that's why I am not writing it over here, correct? I hope this particular part is clear. Any doubts, please feel free to poke me at any point. I'll be moving with the next numerical. Sorry for the bad drawing, by the way. Let me just highlight something. M3 and M4, these are NMOS transistors, and M5 and M6, okay, let me just change the color of the pen, this is not visible, correct? And M5 and M6, so they are PMOS transistors, correct? So this is a question that we have been given. Again we will do the same thing. We will draw the line of symmetry, correct? And we will first try to draw the differential half circuit first, correct? So now let me just draw the differential half circuit, correct? So I had a supply on the top, I have to ground it, correct? Then I have transistor M3, correct, whose gate is grounded because this VB2 and VB1 are short circuited for the small signal analysis, correct? And then again I had what? I have M5, correct? Now if you look at the M5, I will just separately write it over here. This is M5 that I have, correct? Its gate is grounded, correct? Even its source is grounded, correct? Remember the voltage controlled current source was GM times VSG for this particular PMOS transistor. Since the source is grounded, the gate is grounded, that voltage controlled current source will not be present over here, correct? Then how can I represent this particular MOSFET? Remember the model, right? You had this voltage controlled current source and you had R0. Now since this voltage controlled current source is gone, because there is no difference between the source and the gate terminals of the MOSFET M5, I will just represent it with R naught, correct? It's equivalent R naught. So I'm writing it as R naught times phi, R naught phi, correct? And it is connected across this transistor. So now I have connected it something like this. Remember, the source and drain of these two transistors are shorted. So this is the exact same thing that I have done. The drain is shorted to this particular thing, and the source of this M3 is shorted to this particular end over here. Correct? Now I have a transistor M1 on the bottom, source connected to the ground, and then I have Vin over here. And this is where I am taking the output. By the way, I have not written the output nodes. These are the output nodes. Okay. So this is where I have the output. Correct. Now we will see what is the GM of the circuit. So first, if I look what is the GM, entire VGS has been applied. Entire Vin is getting dropped across this gate to source of this particular MOSFET. Correct. So the GM is nothing but GM1. There is no degeneration present. Correct. Now if I write the R out, again I will divide it like Z up parallel Z down. Correct. Z up is basically this thing, and Z down is basically this particular thing. Now what is Z up? So can anyone help me, what will be the value of this Z up? Look,
It will be 1 over GM3 parallel with RO5.
Excellent, very good. I hope it is clear to everyone. Right? Great. So now this is the impedance looking up. What about the Z down? Z down is just R01. Correct? So the total R out will be what? 1 by GM3 parallel RO1 parallel RO5. Correct? And the net GM was this. The net R out is this. The moment you multiply, you will get the differential gain of this particular circuit. Correct? I will just write it. It is minus GM times R out. Correct? This is about the differential half circuit. Now let's look at the common mode half circuit. Correct? So common mode half circuit. Now how to draw the common mode half circuit? I had the supply on the top. I'm grounding it. Correct? Then what about this particular case? Again I will have the RO5 just like I had represented over here. Correct? Remember, the VB is completely independent. The bias voltage are completely independent of whether we are doing the analysis for the differential half mode circuit or the common mode half circuit. Correct? So now, if this is grounded, again the gate to source voltage is completely zero. So again the MOSFET M5 will be represented with just RO5 over here. Correct? Let me just write it. This is RO5 that you have. Correct? Then you have a transistor M3. Correct? Whose gate is grounded now. Now this is connected something like this. Correct? And then you have M1. Correct? And this is V in. Now let's look at the source of the M1. Now what I have written over here, the tail current source is ideal. So what does this mean? There is no R tail that is present over here. Correct? So if there is no R tail, and since I am open circuiting everything that is getting connected across the line of symmetry, the source of the MOSFET M1 will be left open circuited. Correct? This is open circuited. Now can anyone tell me what is the GM of this circuit? Now this is going to be little bit tricky. Be very careful. This is the output. This is the output that I have. Correct? This is the output that I was talking about. So calculating the GM, I may short circuit this and I have to look at the I out that will be coming over. So now tell me the GM of the circuit. Okay, I will help you over here. Okay. Then I'm drawing it for M1. So RO1 is present like this, correct? This node is completely open circuited, and the GM times, what is the VGS of this? GM times V in minus Vx, correct? This is the Vx that I have. Correct? Now, and this is where I am looking at the output. Correct? This is where I am looking at the output. Now tell me what is going to happen over here. This current that you are seeing over here, I will just ask you one question. Can any of this current come out from this particular end? At this, even though I have short circuited over here to calculate the net GM of the circuit, Now I just want to ask one question. Since this other end, the source of the M1 is open circuited, will this current flow out of this loop, or it will keep on circulating within this loop itself to satisfy the KCL?
It will keep on circulating.
Yes, very good. Nothing will come out, correct? And we have already seen this in the last lecture, like what happens when you open circuit the one of the terminals of the MOSFET. We have seen when we were calculating the poles and zeros intuitively, correct? For the active circuits, we had seen this particular case over here, correct? If you open circuit this particular terminal, this current will keep on circulating, because if any current comes out at this particular point, at this particular node, the KCL will get violated. Correct? Because the current that is coming over here, the entire current has to flow back, because there is a current source that is present over here which is dictating you that the same current should come out over here. Correct? So the current flowing out will be 0. Correct? So the GM of this circuit is 0, so it is not giving any gain for the common mode excitation, which is excellent news, because our tail current source is now ideal. So now this is what we are expecting. If the tail current source is ideal, the circuit should ideally completely reject the common mode excitations that I am giving at its input, correct? And this is the good news that we were able to see. I hope this is clear. If any doubts, please feel free to poke me, okay? Now let me move on to this particular case. I will be giving you this as a homework. I won't be solving this completely. Again, if you look, this is a line of symmetry. This is a line of symmetry, correct? Now if I try to write the differential half circuit, if I try to draw the differential half circuit, again I had a supply on the top, correct? Then what do I have? I have transistor M3, correct? I have transistor M3. Then along it I have a resistor that is connected over here, correct? And then this particular node that you are seeing, this is grounded for the differential circuits, right? So this particular node will be grounded. Then I have M1 and then I have V, correct? So now I will just ask you a very simple question now. So now what is the impedance looking up? So by the way, this is VO. What is the impedance looking up? Z up. What do you think?
RO parallel with the
Yes.
RO parallel.
Yes, very good, very good. So the reason is because this, even though it is seeming that this is some kind of feedback, remember this other node is connected to the ground. Correct? This other node is connected to the ground, so that's why we have RO3 parallel R. Now if you look Z down, it will be nothing but RO1. So you can calculate what is the R out net, correct? The net GM of the circuit will be GM1, correct? Entire thing is getting dropped across the VGS of this particular MOSFET, correct? Now when you move on to the now again the next thing is basically I will just give this as a, since I have solved half of the problem, now it is your job to solve this, the common mode half circuit, correct? Now see what is going to happen. This particular end now, correct, this will be left as what? This particular end will be left as open circuited. Now before giving you a homework, I will just ask you a simple question. Since the other end of this resistor is open circuited, will this resistor play any role while determining the gain of the common mode half circuit?
No.
No, right? So that is the hint. Now we have already solved a question like that, correct? When the other end of the resistor was open circuited. So now you can solve the common mode half circuit yourself. If you have any doubt, please come back in the next lecture. I will be able to help you over there. Correct? So now any doubts? Yeah.
Sir, is there any advantage for this circuit? It is like the gain is almost GM1, R0 and R0 1 only.
Good. So that's a very good question. The thing is, if you look at the bias point of this, correct? Then the
Self bias.
Yes, now it is a self bias. Remember one problem that we had solved, right? We have looked at this structure. This is what we call as a CMOS inverter, right? The problem with this was when you give at the output, the bias point is very poorly defined. Any mismatches between the VTH of the PMOS and the VTH of NMOS can easily derail the biasing point over here. Ideally, I want this biasing point to be around what? Around VDD by 2, so that I can get the maximum symmetric swing along this particular point. Correct? Now this bias point is poorly defined. Correct? And I don't want this bias point to vary with the PVT. So what did I do? I inserted a resistor over here, very large resistor. correct? Now what did it do? It basically did what? Remember the transfer characteristics of your CMOS inverter. It used to look something like this. This is very very bad. Really sorry for the bad drawing, correct? What this resistor did is basically enforce the condition that V out is equal to V in. So if I draw a line V out is equal to V in, so now even after the PVT variations and all, at least you are sure that your circuit is now biased at this particular point. So these resistors are helping and doing the exact same job, just like what you said over there. Is it clear now? Guys, is it clear or
You're not audible.
sorry?
You are not audible for last 1 minute or so.
I was
when you
not
told
audible.
that our large
Okay.
is very large.
Okay, yeah. So what I was saying is, if you look at I was just trying to give you an analogy that we had looked at one similar circuit where we had inserted this resistor. So now the thing over here is, if anything at the output, if I had not inserted this R large, correct, then the DC point at the output is poorly defined. What do I mean by poorly defined? Just look what is setting the output biasing point. The VDSAT, the overdrives of this PMOS and NMOS transistors, correct? Can the overdrive voltage, I will just ask you one question. The VDSAT is what? VDD minus, what you can say, not like this, wait. The output DC is basically VDD minus VDSAT of the PMOS. Correct? Now I will just ask you simple question. Can the overdrive, the VDSAT of the PMOS vary with the PVT, with the process voltage and the temperature variations? Can VDSAT vary? Yes, because this contains a term, right? The threshold voltage. If I talk about the PMOS, it is VSG minus mod VTP. Correct? The threshold voltage easily varies with the PVT. Correct? Now that is what I was talking about, the poor biasing of the output DC point. Correct? So now what we did was basically we inserted a huge resistor between the input and the output. What it did, it enforced the condition that the input and the output, right, it will be always equal. Now the thing over here is, now the thing that is actually happening, I'm talking about the DC point over here. So now if the output and the input's DC point is equal, so this is where I have enforced the condition. This is where I have fixed my operating point now. Correct? So this is where I have fixed my operating point now. Now any small signal that is present around the VIN, correct, around this particular range over here, now the bias point is fixed. Correct? The bias point is now not poorly defined. Now come back and again apply the same analogy over here. Correct? These resistors are helping you to fix the biasing point that is present over here. They will make sure that this particular point is as much as PVT invariant as possible. So this is a job of the R resistors that we have placed over here. Is it clear?
Yes, sir.
Yeah, very good. So now let me just see how much time do we have. Okay, so
1 hour.
Yeah, 1 hour. Good. So now we will be moving on to the concept of let me see. Yeah, I guess I have to take this problem at the end. Let me just see, because I have to cover one more problem which is a complete design problem, and I will give a high weightage to that particular problem. We will see if we can solve this problem towards the end. Okay. Now I just wanted to talk about the input and output common mode ranges. So now first of all we will look at the two examples. We just looked at the 5 transistor OTA, the 5 stage OTA, the circuits, the current mirror load that you are seeing which is applied across a differential pair. So that is usually called as the 5 stage OTA, right? The single stage op-amp. Now the thing is, I can design a counterpart of it, correct? What do I mean by the counterpart? So now I can use a PMOS differential pair, correct? I can use a PMOS differential pair and then put what? Then put NMOS current mirror load. NMOS current mirror load. Now what is the advantage of doing this, correct? Now just ask yourself a question. In which cases I prefer to use a PMOS differential pair, correct? You remember the flicker noise, right? You remember your flicker noise. Now when I want to design a circuit which is having a low noise, like it is having a low input referred noise, correct? You had seen the factor K upon omega L Cox 1 by F. And sir has also told you that this K, right? This K, so this K is greater for NMOS than the PMOS. Correct? And why does it happen? the way usually the holes do not face that much trapping and detrapping in the silicon to silicon dioxide interface as much as the electrons faces it. And how can you prove it? Basically, you have to draw the energy band diagram of the MOSFET along the vertical cross section, correct? And then you will see that it is far much easier for the electrons to get trapped into the oxide than for the holes to get trapped into the oxide, correct? So now whenever you want to design a circuit for low noise applications, correct? Low noise applications.
Is it not because of mobility, bro?
Sorry.
Mobility of n-type will be greater than.
This K.
Is
Okay.
it not because
Okay.
of mobility?
No. The
K
thing is, it is not completely because of the mobility. See, if you look at this expression, right? Mu is not present over here. This K that you are seeing over here, the formula for K, at least I have not seen it in most of the books. It is written empirical fitting. Correct? So the primary reason, I am not sure how much it is dependent on the mobility. So if you have the same question, then I will ask you one more thing. Now just change the technology from silicon CMOS, just move to maybe gallium arsenide or something, or maybe some other technology where you will still have traps that will be present in the oxide to semiconductor interface. Correct? So I am not sure how does this K depend on the mobility, because I don't know the formula for this, correct? But I can 100% tell you that it is not mainly because of the mobility, it is because of this factor K that is present over here. And the formula for this, I literally don't know. I have to look at it. Maybe I can get back to in the next lecture.
I think for Kn it will be mu and COX WIL.
No. See,
Okay.
this K is not that. See, if you look at ID, you are talking about this, right?
Current
Mu and
factor.
COX W. This K and this K is completely different. They don't have any relation. They don't have any relation. Do not confuse that this is the same K that you are seeing over here. These two Ks are different.
Okay, bro. Okay.
Yeah, this is different. Yeah, just remember that. Now coming to the question, how does this K depend on the mobility? I have to check. I don't know the formula for this. As far as I remember, when I did last time, it was mentioned as an empirical fitting parameter. And if it is empirically fit, literally there cannot be a unique formula. That means the way the TSMC fabricates this semiconductor, the oxide to semiconductor interface, and the way UMC may fabricate or the global foundry fabricates, it will depend on the way they are fabricating. If the TSMC's this oxide interface is very, very pure, the flicker noise that you will get in the TSMC's MOSFET, right, it will be lower than what you may get at the UMC or the global foundries MOSFET, correct? This is what actually I was talking about. This K is basically telling you the quality of this interface, the silicon to silicon dioxide interface, correct? So this is what I was talking about. And remember, mobility gets degraded because of it. I don't think mobility depends on the, I don't think this K depends on the mobility. It is actually opposite. If there are a lot of traps or there is a lot of roughness in the silicon to silicon dioxide interface, remember, because of this roughness, your mobility can degrade, correct? Your electrons are moving with a high field. If they see such a roughness, the effective velocity, it will get reduced because of this roughness, scattering, and the mobility will degrade because of this roughness, correct? So this K is representation of this roughness. This is what you can think of intuitively. Okay, so now this, I hope this particular part is clear. Now for the EEG and ECG signals, right, you need an extremely low noise. So there is a thing called as, basically we are actually putting some sensors on human head and we are trying to get the EEG signals and all, correct? So some neural interface circuitry, a huge research is going on over there, correct? Now these signals are very weak, correct? And now if you don't want to decrease the SNR by introducing a lot of noise, you have to use a PMOS differential pair to make sure that you do not introduce a lot of noise in the signals. Now why does it matter so much? Because remember, the flicker noise troubles you when the spectrum of the flicker noise is till flicker noise corner. Your flicker noise will dominate, after it your thermal noise will dominate. So if my signals are lying at the very, very low frequencies, then this flicker noise will affect me very heavily. What is the frequency of this EEG and the ECG signals? Is it high or is it very low? You know this, right? 72 bits per minute. So the frequency is nothing but 72 by 60 hertz. Is it very low or it's high? Guys, are you able to hear me? No.
It's very low.
You're audible, sir.
I'm audible, right?
It's very low frequency.
Yeah, it's very low, correct. So, just a minute. Yeah, it's very low. So, that is the reason why you can see in this particular region over here, your flicker noise will actually kill it will actually kill whatever effort you had inserted to improve the SNR. Correct? So, that is what I was trying to say. Now, let's look at this PMOS differential pair first. So, now this circuit sir has already analyzed, correct? How does the input common mode range and output common mode range is? So I will just try to cover this topic very quickly. So now let's see the limits on V out. Correct? Let's see the limits on V out. So now if I talk about the upper limit, what will happen if I keep on ramping the V out very high? Which MOSFET is going to trouble me? Which MOSFET will be going into the triode first? Just look at this particular point. There are only two transistors, M4 and M2. If I keep on ramping the V out, will there be any effect on the M2? Can M2 go into the triode because of ramping in the drain voltage? Guys, are you not able to hear me?
Yeah.
What will happen if I raise the drain voltage over here? Can M2 go into the triode? What about the M4?
M4 will go to the triode.
Yes, M4 will go into the triode because remember the triode condition for this is nothing but VD should be less than VG plus mod VTP. Correct? If I keep on ramping the VD, the V out node over here, this condition may become violated. Correct? So I hope that particular part is clear. So basically your V out, correct, should always be less than or equal to VDD minus VD sat 4. Correct? So this is placing an upper bound. Now coming to the lower limit, what will happen now if I keep on decreasing the V out? What will happen? Can M4 get into trouble now?
M2 will be affected.
Yes, M2 will be affected, right? So this condition is dictated by what? Dictated by M2. Going into where? Going into the triode region. Correct? There will not be sufficient headroom that will be left over. Correct? So now if you look at so if I write the condition, right? So what will be the condition? The VD should be greater than or equal to VG minus VT, the V bias minus VT, 2 or 1. Correct? So the limits on the V out, if you write, they will be what? VDD minus VD sat 4 on the upside, and on the lower side I have this particular limit, right? V bias minus VT 1, 2. So this we have already seen. Now coming to the limits on V bias. Now just think about it. What will happen if I keep on ramping the V bias? So let me look at the upper limit first. So if I keep on ramping the V bias higher and higher, now what is going to happen? You know that from analysis, correct? These two nodes that you are seeing over here, correct? They have to be equal, or else there will be a contradiction that will be created, which sir has already explained in the lecture, correct? It will take a lot of time. I don't want to go into it. So now these two nodes has to be equal, correct? These two voltages have to be equal. So now the thing that is going to happen is if you keep on increasing the V bias, correct? If you keep on increasing the V bias, then the problem is this M2 will actually get into trouble, correct? Because you are continuously increasing the gate voltage, but the drain voltage that you are seeing over here, correct? The drain voltage that you are seeing over here, these drain voltages are not changing, correct? The thing that may change is this particular thing, correct? I'm not talking about the small signal, okay? I'm talking about the DC points. So don't think that this is at the small signal ground. We are talking about the DC voltages. This will have some finite DC voltage over here. correct? So if this voltage is not changing, if this is continuously getting increased, then what is the dictating condition on M2? VD of M2 should be greater than VG minus VT, correct? VG is V bias. So if I keep on ramping the V bias higher, and if the drain voltage is not changing, correct, then the problem is this condition will get violated, it will enter into the triode region, correct? So if you dictate this condition, then what will be the upper limit that I can put on the I can put on the V out, correct? So now the way to do it is basically, if I look at the M1 now, so now this particular transistor, right, there are two things. There is a VSD of M3 and there is a VSG of M3, correct? I am not worried about the VSD of M3 because VSD was used to ensure that the MOSFET remains in the saturation, but the moment the gate and the drain of the MOSFETs are shorted, as long as the VSG of the MOSFET is greater than the threshold voltage, I always know that this MOSFET will always be in the saturation, correct? This MOSFET will always be in the saturation, correct? So when I'm moving from this particular point to this particular point, right, I have to take into account VSG, not the VSD, because VSD was used to check whether the MOSFET is in the saturation or not. If this is getting difficult, just let me know, because this is very important. The books will not explain you why VSG3 was taken, why VSD3 was not taken, why VSG3 was taken over here, correct? This is extremely important, and let's see which is the stronger condition, correct? So for VSG, right, this VSG has to be greater than or equal to, I have to make sure that it is greater than or equal to mod VTP, correct? Only then the MOSFET will be on, and when the MOSFET will be on, correct, then I am ensured that this MOSFET will be in the saturation. But along with that, the way we design it, we usually keep some headroom, right? We usually keep some headroom across this MOSFET as well, correct? So VSG3 minus mod VTP was what? VSD sat, correct? VSD sat of 3. So VSG3 is what? VSD sat plus mod VTP, correct? And why do we have this VSD sat over here? Remember, we keep some headrooms, right, across the MOSFET. We keep some headrooms. If you keep a headroom over here, if you don't keep a headroom over here, then that is not good. We want to make this circuit as symmetric as possible, correct? So whenever you are trying to enforce a condition over here now, correct, you are trying to do what? You are trying to get the upper limit, and that will be dictated by what? The upper limit will be dictated by M1 or M2. And limit on what? Limit on V bias I'm talking about, correct? The limit on V bias. So now this particular voltage is what? This particular voltage is VDD minus VSG3, correct? It is VDD minus VSG3. What is VSG3? VSG3 is this particular expression. So this is what? VDD minus VSD sat of 3 minus mod VT3, correct? This is what I have. Now what I have to ensure is that this drain voltage, right, this is what? This is drain voltage of M1. Now drain voltage of M1 has to be greater than or equal to V bias minus VT1, correct? So the VD of M1 is what? This VDD minus VSD sat of 3 minus mod VT3 has to be greater than or equal to V bias minus VT1, correct? So this long expression will yield upper bound on the V bias, correct? And that bound will be what? It will be V bias should be less than or equal to VDD minus mod VT3 plus VT1 minus VSD sat 3. So this is the upper bound. Guys, any doubts? This is extremely important. Any doubts at this particular point? Is it clear or going above your head? I need at least some feedback over here.
Can you explain again?
Okay, sure. So see, now we are actually doing what? We are trying to determine the upper limits on the V bias. Where are we applying the V bias? At the input of the transistors M1 and M2. Correct? So now this is where I am trying to find the upper and lower bounds on the V bias. Correct? And the reason why we are doing it is because at the input I want to see what is the voltage level up to which I can work. I cannot apply a VDD voltage over here. correct? I cannot apply a zero voltage at this input, correct? I have to have a fixed range, and this fixed range will be determined by the MOSFETs going into the triode. If I make sure that all my MOSFETs remain in the saturation, correct, then that is the range where I can apply my input now. So now what we did is basically we try to find the upper bound on this V bias, correct? And how did we do it? So first I did a thought experiment. What will happen if I keep on increasing the V bias, correct? Then the thing is, if you keep on increasing the V bias, right? If you keep on increasing the V bias, then the thing is, this MOSFET M2 will get into trouble. Why it will get into trouble? Because these node voltages that you are seeing over here, they will remain fixed. If they start changing, right? If they start changing, then there will be a contradiction, which sir has already explained, that we usually expect what? I0 by 2 and I0 by 2 current to flow over there. Correct? Now if these two voltages become different, right? Now the pair will not work in a symmetric manner. Some extra current will be flowing over here, and the thing is that extra current will get dumped into this transistor as well because of the current mirroring action. We have a current mirror load over here. So if more current flows through this particular branch, if this current mirror was not there, then the less current would have been flowing through this particular branch. But now this more current which is flowing, first of all, this current, the higher current is itself is getting replicated from M3 to M4, and that higher current is getting dumped over here. Correct? What we were expecting is some should be remaining I0, right? The current flowing through the left branch and the current flowing through the right branch, its sum should be I0. Correct? Now if this voltage increases, then the thing is, what we expect is basically because of the channel and modulation, correct, the current through M1 should increase because of the increase in the VDS of the M1. Correct? Now if the current increases, then ideally if the left side current increases, then the right side current has to decrease, correct? Because I am operating under the right conditions. I have placed my bias points such that my circuit, all the MOSFETs are in saturation. Now the thing is, if the I right should have been decreased, but remember the increased current of the M1 is getting current mirrored from M3 to M4, and again that is getting dumped into the right hand side branch. So right side current is also increasing now, the left side current is also increasing now. Now if both the current increases, can there some remain I0 or not? Just tell me this.
Both the currents are increasing, it won't be I0, bro.
Yeah, it need not be I0. First we started with assuming that the sum of these two is I0 under the right conditions. Now the reason why I am telling you this is because I guess the confusion arose why these 2 points has to be at equal potential, correct, and why they should not change, correct. That is where I guess the confusion got created. So I was skipping that part, but that is the part that I have explained right now over here, why these two nodes should be at a equal potential, or else this condition that you are seeing over here, we are contradicting ourselves only. If the current on the left branch increases, then the right current should have been decreased, but you remember the increased current in the left branch is getting current mirrored, and that increased current again is getting dumped into the right branch. So if one of the current increases over here, the right hand side current will also increase, and then their sum will not remain I0 anymore. We are doing the constant current biasing over here, remember. So that is why these two nodes has to be at a equal potential. Now once this is clear, now let's understand what the conditions have imposed over here. So now I'm trying to find the upper bound on the V bias, correct? Now V bias can put me in trouble. V bias can put me in trouble because these two currents has to remain I0, so this potential cannot change even if I change the V bias over here. Just remember this, if I change the V bias, this potential is not allowed to change now, correct? This potential is not allowed to change because of the reasons that I had explained. Now if this node voltage does not change, and if I keep on ramping the VG higher, then what is the condition for the saturation of the MOSFET? VD should be greater than VG minus VT. If the drain voltage remains fixed but the bias current increases, you can see that at one point this condition will become violated. So the upper bound on the V bias will be dictated by M2 or M1. Anything you can take, okay? Anything you can take. I am taking M1 over here. Now the thing is, if I look at the M1, what is the drain voltage? What is the fixed drain voltage that I was talking about? This is nothing but the VDD that is present and the drop that will be happening over here, correct? So that drop, I had explained that it is actually VSG3, correct? That drop is VSG3 because remember the gate and the drains are shorted over here, correct? So that is why we are taking VSG3 over here. And why are we taking it? Because VSD3 does not matter over here, because this MOSFET will always be placed in the saturation because gate and drain are shorted together. Remember, any MOSFET whose gate and drain are shorted, you just have to ensure that VGS is greater than VTH. The MOSFET will directly turn on in the saturation. It will never go into the triode if its gate and drain are shorted together. Correct? I assume that you have studied this in your analog electronics course at least, correct? When you had studied about the current mirrors. Now once you apply this condition, correct? So this is what I was applying. The voltage that is present at this particular point, I have to find it first, correct? So how can I find it? This voltage is basically nothing but VDD minus VSG3. Just track this node, correct? VDD minus VSG3, correct? VSG3, this is the source point, this is the gate point that I have. So VDD minus VSG3 is the point that I have. Now to find this, I have to first find the VSG3 as well, correct? And how can I find the VSG3? The VSG3, I remember the only thing is that some VD sat, the VSD sat for the PMOS and the VD sat for the NMOS is fixed in the design, correct? So the VD sat is nothing but the VSD sat is nothing but VSG minus VTH, that is mod VTP over here. So the VSG3 is nothing but one threshold voltage plus one overdrive voltage of the PMOS. So this is the VSG3, and why are we finding it? Because the drain voltage is remaining fixed. Since the drain voltage is remaining fixed and the gate voltage is I am ramping it up, correct? I have to find the upper bound on the V bias such that this MOSFET is just at the edge of the saturation, correct? And now to get that, I have to find the value of this particular point, the voltage at this particular point. The voltage at this particular point is VDD minus VSG3. To find the VDD minus VSG3, I have to find the VSG3 first, correct? Now to find the VSG3, I have written it in terms of the overdrive voltage, because this is what usually designers give, 100 millivolt or 200 millivolt. Now once this VSG3 fixed, now the VDD minus VSG3 value is this particular quantity over here. This particular quantity that I am highlighting over here. Right? Now once this is fixed, I have to make sure this is what? This is the drain voltage of M1. Now this drain voltage of M1 has to be greater than the gate voltage minus the threshold voltage to satisfy the saturation condition. This condition I have written over here. Correct? This condition I have written over here. Now VDM1 that I have written over here, you will substitute the with this particular condition. We have already found out what the VD of M1 is. This is the VDM1. Correct? Now when you put this expression, correct? When you put this expression VDD minus VD sat minus mod VT3 in over here, this is what I have represented in the last particular line of this particular page. Correct? And now you can see that the V bias is present on the right side, and now this V bias is facing some upper bound. Correct? And this upper bound I have written like this over here. So there is some upper limit that came on the V bias because your drain voltage was not changing. It was remaining fixed because of the fixed overdrive voltage of this particular MOSFET. Correct? And you kept on increasing the V bias. So what happened was the gate voltage increased, the drain voltage remained same. So this MOSFET went out of the saturation, and this is the upper bound that we are able to found now. Any doubts now? Any doubts at this particular point? Is it clear?
Yes, bro, clear.
Yes, very good.
Yes.
Yes, excellent. So now once this is clear, so now we have found the upper bound on the V bias, correct? Now we will try to find the lower bound as well, correct? So now let me find out the lower limit. So the lower limit I will try to find out now. So now let's see what can actually cause the lower limit on this particular MOSFET. Let me change the color of the pen. पूरा खिचड़ी बन गया यहाँ पे. Just give me a second. Yeah. So now if I try to find out the lower limit, correct? We are trying to find out the lower limit on V bias. So now just look at this particular net, okay? Now if I reduce the V bias, correct, then this MOSFET cannot go out of the saturation because the drain voltage is fixed. If I am reducing the gate voltage of this MOSFET, I am actually helping the saturation condition to enforce, correct? The VD should be greater than VG minus VTH. If I reduce the gate voltage, then MOSFET cannot go out of the, what you can say, saturation region at least. Now there is some other condition that will come into the picture, correct? Now if I keep on reducing the V bias, correct, just remember that this transistor that you are seeing over here, correct, this particular transistor, it needs certain headroom across it, correct, to function as a current source, because this MOSFET has to be kept in the saturation. One more question I would like to ask you: if this M0 goes into the triode region, can this MOSFET act as a constant current source or not? Just tell me that.
No.
No, right? Why it will not act as a constant current source? Remember, in the triode case, right, the MOSFET act as a voltage dependent resistor. Any change in the voltage that you will see over here, the current that you are seeing over here, it will not be a constant current source. Even if you are trying to distribute the current, it will be, the current value will be changing with the signal swing, and that is a very bad current source, correct? I don't want that to happen, correct? So I have to keep a minimum headroom over here. And what is the minimum headroom? Remember, this MOSFET needs VD-SAT 0 voltage to remain in the saturation region, correct? So that means what? If you look at the source of M1, correct? Now the source of M1 cannot go below VD-SAT 0. Correct? The source of M1 cannot go below VD-SAT 0. Correct? I hope that particular part is clear now. So now what we have to ensure is, if I move from this V bias, right, I will just write M1. I will just draw M1 over here so that it will become very much clear. I was applying V bias over here. Correct? There is a bound that I have placed, VD-SAT of 0. Correct? Now, what is the condition now? So basically V bias minus VGS of M1. Correct? It has to be greater than or equal to VD-SAT 0. If this condition does not persist, then the MOSFET, the tail current source that you are seeing over here, it will go into the triode region. It needs VD-SAT 0. Correct? It needs at least VD-SAT 0. So now VGS, so now what I will be doing is, I can again write V bias as what? V bias should be greater than VD-SAT 0 plus VGS of M1. And what is VGS of M1? Remember, how did we calculate the VSG of 3 over here? It was nothing but basically 1 overdrive voltage plus 1 threshold voltage. Correct? 1 overdrive voltage plus 1 threshold voltage. Similarly, I will be doing over here. V bias is greater than or equal to VD-SAT 0 plus 1 overdrive voltage of what? M1. VD-SAT of M1, correct? I am just writing it as VD-SAT 1 plus threshold voltage of 1. Correct? So this is the lower bound that I have placed over here. And remember, this VD-SAT 0 and VD-SAT M1, correct? This tail current source is biased. It is carrying, the MOSFET is carrying the current I0. The M1 and M2, correct? The M1 and M2 that you are seeing over here, this current is getting divided between both of them. Correct? So the biasing condition of M1, correct? The equilibrium, the quiescent operating point, the current flowing over here is I0 by 2. For M2 also the current flowing over here is I0 by 2. But remember, for I0, this particular MOSFET, M0, the current, the quiescent current itself is I0. So whenever you are designing, just take this into account, okay? Or else your answers will come out to be wrong. So now the final bound on the V bias, correct? The final bound on the V bias was VDD minus VT3 plus VT1 minus VD-SAT 3, correct? And on the lower bound, I have what? The VD-SAT of the tail current source plus VD-SAT of the M1, correct? VD-SAT of M1 plus threshold voltage of M1. So now what you can see, this is the range that I got for the input. So what I have to make sure, my input signal will not exceed this range. Okay, it is my duty to ensure that my input signal will not exceed this range. Correct? And this is what we call as what? Input common mode range, ICMR. And similarly, we had seen the bounds on this, correct? The upper limit was this on the output and the lower limit was this. So this bound that you are seeing over, this is called as the output common mode range. Correct? So now remember that we are not taking into account any signal swing. Correct? So what I am assuming is that the V bias, around it some small signal is present, very small signal, correct? Now if this signal becomes larger, I have to make sure that this signal swing, right? This signal swing is accommodated within this input common mode range. What do I mean? Let's take one example so that everything becomes clear, correct? So now let me take one example. So let me put some numbers over here. So if you take 180 nanometer CMOS technology, usually the supply voltage is what? VDD is 1.8 volts, right? The VDSAT, it is dependent on the designer, but usually we will keep it around 200 millivolts to keep a very robust design, correct? VTH of PMOS, I'm assuming to be equal to NMOS just for this particular case. Some 50-60 millivolt variation will be there, but that does not matter over here. I'm assuming it to be 500 millivolts, correct? So now let's look at the input common mode range. This particular bound that we had placed, right? So what is VDSAT? VDSAT for all transistors is 200 millivolts, correct? So VDSAT of 0 is 200 millivolt plus VDSAT of M1 is 200 millivolt plus one threshold voltage is 500 millivolts, correct? This should be less than or equal to V bias. This should be less than or equal to, what is VDD? 1.8 minus what is one threshold voltage? This is 0.5, correct? What is again VT1 over here? Again 0.5. And what is one VDSAT? VDSAT is 0.2, correct? So now if you calculate this, this is 200 plus 200 plus 500. So how much is it coming? Let me just see if I have made any mistake over here. By the way, yes, there is a mistake. So this should have been minus because this is mod VT1. Let me just check. Let me just check. This was a transistor 1, right? I was working with the transistor 1. This is not a PMOS transistor. This is a NMOS transistor, right? So this is not any. So this is true. There is nothing. This mod you can remove because this was the threshold voltage of NMOS only. Correct. So now let's look at the NMOS case. So now if you look, what will be the input common mode range? So this 200 millivolt plus 200 millivolt plus 500. This will become what? 0.9 volts. Correct. This became 0.9 volts. And similarly, on the upper bound, if you look, what is this upper bound? This is around what? 1.6 volts. So now what you are seeing over here is your sinusoid that you are applying at the input along with the DC level, right? So this entire thing from peak to peak I'm talking about, correct? So you biased it somewhere, correct? Now this upper limit should not exceed 1.6 volts. This lower limit should not go below 0.9 volts for very good operation. If you don't want any non-linearity to be there in the signal, then you have to respect these boundaries. That upper point should be at 1.6 max to max. The lower point should be at 0.9 volts. Only then you can ensure that your circuit will amplify the signal properly. Is it clear now what is this ICMR, or some doubt is still there in this? Any doubts? Is everything clear about ICMR and OCMR, the input common mode range and output common mode range?
Yes.
Okay, excellent. So now once this is clear, I guess we are good to go with the design problem now. So yeah, I wanted to cover it, but unfortunately I don't have time. While uploading the notes, I will solve it, and you can look by yourself. If you have any doubts, then please feel free to come back in the next lecture. If you have understood how I had derived the conditions on the upper bound and the lower bound on this V bias as well as the V out, this should not be a trouble. Okay, you should be doing the same analysis and you should be getting the almost same answer. The only thing is why we are working with this PMOS diff pair over here is, remember, the ICMR over here came from what? In the previous case, the ICMR came around 1.6 volts to 0.9 volts. Remember, now in the case of the PMOS pair, since you have a NMOS current mirror load, right? What you will see over here, this ICMR was biased towards the VDD. What do I mean by biased towards the VDD? Remember, 1.6 volts is just 200 millivolts away from VDD. Correct? But 0.9 volts is 900 millivolts away from the ground voltage. This is what I mean by the biasness of the ICMR. Correct? If you look at the PMOS pair now this will look something opposite. Now if you calculate the ICMR, it will come out to be something like this. Okay, now the ICMR is biased towards the ground. correct? Why? Because the lower limit is hardly 200 millivolts from ground, correct? Whereas if you look at the higher limit, it is almost around 600 millivolts from VDD, correct? Now, can you combine both of them intelligently? What do I mean by that? From the PMOS differential pair, correct, I'm able to cover the lower voltage range for the input. With the NMOS differential pair, I am able to cover the higher range, correct? I am able to cover the higher range for the input. Now if I smartly combine both of them, right, can I get a voltage range for the ICMR which will look something like this, correct? Which will look something like this. And yes, people have done it. You can combine both of them intelligently, and this is what is called as rail to rail op amp. Okay, this is what is called as the rail to rail op amp. Just search on the Google. The circuit will look little bit complicated, but if you analyze this circuit first, and we have already analyzed the NMOS differential pair with the PMOS current mirror load, right? Sir has already analyzed it. Now, after analyzing both of them, now if you search this rail to rail op amp, now you will be able to understand why the rail to rail op amp topology was chosen like that. Correct? So this was done to make sure that the output common mode range and the input common mode range should be, the lower bound should be as close to ground as possible and the higher bound should be as close to VDD as possible. So this is one of the applications of it, and that's why I wanted to cover this particular part, but no worries, I will solve it while uploading the notes. Okay. The most important part for today's lecture is this particular design example that I had taken from problem that was posted by Professor Imon Mundal from IIT Kanpur on the LinkedIn. So this problem was posted for a position, the project associate or the research associate position at IIT Kanpur. Correct? They wanted to hire a person, and to hire that, so they gave a person 1 week of time and they told him to analyze this circuit and solve whatever they are demanding over here. Correct? So now what we have to do is, I won't be able to solve complete problem, but at least I can solve most of the stuff, and I can at least direct you how you can solve the rest of the problem. Correct? So what this circuit is, you guys can easily analyze, and you guys should tell me what this circuit is. What does this circuit look like to you? If you consider this as an ideal op amp, yeah, this is OTA, okay. But what about this entire circuit? How does it looking like to you?
Inverting amplifier.
Yeah, it is not this is VI. I guess it is my bad that the image is zoomed out. The input is applied to the positive terminal, and this particular point there is just V bias that I have applied over here. So input is applied at the positive, and this is the feedback that you are getting. It is connected to the negative terminal. So it's not a inverting, it's a non-inverting amplifier, right? So now for this non-inverting amplifier, they have given me the specs over here. The VDD is around 1.8 volt. Why 1.8 volt? Because the PDK that was given for this particular problem was TSMC 180 nanometer technology. Okay, so that's why VDD is 1.8. The load capacitor they have given as CL, and it's 10 picofarad, very huge capacitor, right? Why huge capacitor? Because this block may be driving some input of the analog to digital converter, and depending on the sizes of the transistors that are used inside the ADC, they can present a very huge load over there. Correct? You remember it has some sample and hold circuit as well, and it has other circuits as well inside the ADC. So the cap can literally go to this particular value. The loop gain, correct? The minimum loop gain that they are expecting for this circuit is 40 dB. 40 dB means 100, correct? In volts by volts term, correct? Volts by volts term. The 3 dB bandwidth of the loop they are asking me to design is 100 megahertz, and the CMRR that they are asking is around 80 dB at DC. Correct? Now, you remember we had done this kind of problems, but we had not delved into the transistor level design. You remember we had solved the problems. A few specs I have given. I had solved it using the feed forward op amp. I had solved it using the dominant compensation, as well as I had solved it using the Miller compensation as well. Correct? Another thing, if you look, we had also solved the problem for the TIA design, the trans impedance amplifier design, which was designed for the state of the art data centers, right? So the problem, reason they are giving this kind of problem is, first you have to design a circuit like this. Now from this particular specs, our job is to get the W by L ratios for these transistors, correct? So my job as a circuit designer is, whatever information is given over here for this particular circuit, I have to extract the GM, the net GM and the net R out of the circuit, correct? Once these are extracted, then I have to also extract the I naught, correct? I have to get the I naught for this circuit as well, correct? And once I am able to extract from all the loop gain analysis and whatever values they have given over here, if I am able to extract the capital GM, what is the capital GM of this circuit? This is a same circuit that we have been looking at for this particular week. What is the GM, the capital GM of this circuit?
GM1.
Yes, GM1, exactly. So also if you look at the R out is nothing but RO4 parallel RO2, correct? If you assume RO4 to be almost equal to RO2, this will be around what? RO2 by 2, correct? So you can see that the specs on the capital GM and the capital R out, that will come from the gain, the loop gain analysis, correct? They will dictate what is the GM of the transistor that I have to make sure that the GM of the transistor is sufficient, correct? It will also dictate a spec on the R0 too, correct? Output impedance, correct? I0 I have to get it somehow, correct? I have to get it somehow. And the moment I know the I0 and the GMs of this, correct, along with some ICMR ranges, correct, ICMR plus, ICMR minus, if these specs are not given, ICMR plus, ICMR minus, because these are usually secondary specs. So what are the secondary specs? I will tell you. The slew rate of the op-amp, how quickly, if you give a very large signal at the input of the op-amp, how quickly can its output ramp up with respect to its input, correct? So the dV0, the how quickly the output can change with respect to time, this is what the slew rate is. Then we have already seen ICMR plus, we have already seen ICMR minus. So these are usually what I call as a secondary specs, because in many design problems these specs are usually not given, correct? In many design problems usually these specs are not given, and if these specs are not given to you, generally what we do, we have to assume some values, correct? What values we have to assume? For slew rate, maybe you can assume something like 100 volt per microseconds, right? 100 volt per microseconds. For ICMR range, we have already seen, right? What is the ICMR range value that we had got previously? The ICMR range that we had got previously was from 0.9 volts to 1.6 volts, correct? From 0.9 volts to 1.6 volts. So again, I will just improve it a little bit over here. ICMR plus to ICMR minus range, I will take maybe from 0.8 to 1.6 volts. Correct? Now why are they so important? Remember, ICMR plus and ICMR minus will dictate the overdrive voltage of this M4 and M3. Correct? Now you guys tell me, if I know the current that is passing through M3, correct? And if I know the VSD SAT of M3, can I get the W by L ratio for M3 or not? Just tell me this.
Yes.
Yes, right? How will I get it? Of course, you definitely know. What is this? ID is basically what? Half mu
mu1
Yes, yes. Very good, very good. W by L into this VSD SAT whole square or overdrive voltage square. You know VSD SAT, you know ID, you know mu p Cox. From where will you get the mu p Cox? For that, they have given you this PDK. Correct? The TSMC 180 nanometer technology. Correct? Now from here, you have to see whether you can find out the value of mu p and mu n or not. So from here, you have to find those values. How will you get the Cox? The Tox, the thickness of the oxide has been given to you over here. Correct? The thickness of the sorry. Can you repeat?
Permittivity of oxide.
Yes, excellent.
Thickness.
Epsilon ox by Tox, very good. So from here you will get the Cox, and epsilon ox you already know, right? It is nothing but epsilon naught into epsilon r. Epsilon r is around 3.9. So from here you can get the Cox. Now mu naught is given over here. Okay, this is u naught. By the way, to get familiar with these symbols, this is going to be a little bit challenging. I will just refer you one book. You may be knowing this book, I guess. Digital. Let me just search the title of the book. I guess it's CMOS VLSI Design by authors Neil, West and Harris. Okay, just refer this book to get familiar with the symbols, or maybe you can look up to some PDKs, some online articles you will be able to see which can describe you this, correct? So from here I can get the value of mu n, mu p and Tox, correct? And from the moment you know this, correct, you can get the value of mu p Cox, and from here I can get the W by L ratio for this. And remember, how will you choose the L of this? How will you choose the channel length? Remember, what did I tell you? Unless and until your 3 dB bandwidth exceeds like 600, 700 megahertz or 500 megahertz or 1 gigahertz, right? You absolutely don't have any reason to design the op-amp with the minimum channel length, correct? Remember, the minimum channel length is a curse for analog designers. Why? It will degrade the R0, correct? It will degrade the R0. It will degrade the matching. Why it will degrade the matching? Because area will be less. Area will be dependent on the product of W and L, correct? And third, it will degrade the current mirroring action. It will degrade the current mirroring action. You remember, if you have not studied this, let me just help you with this. The I2 by I1 ratio, correct? You may have seen that it may just depend on W by L ratios of transistor 2 and 1. But remember, if your transistors suffer from the channel length modulation, you just cannot ignore this particular factor. Now you guys tell me what happens to the lambda if I keep on reducing the channel length. Lambda will become significant or it will become insignificant? As I reduce the channel length, what happens to the lambda factor?
It will increase.
Yes, it will increase, right? And if lambda increases, remember, your output impedance was what? It was 1 by lambda ID. So for the same current, if your lambda increases, your output impedance actually decreases, correct? So that is what I was seeing over here. Ideally, these two factors, right? This particular bracket that you are seeing over here, this should have been ideally 1. But because I decided to choose a minimum channel length transistor, I got a higher value of lambda, and now my I2 by I1 ratio will vary with the drain to source voltage, which is a very bad thing, correct? Which is a very bad thing. So that is why I was saying that the minimum channel length is a curse for analog designers. Unless and until you are designing the extremely high speed circuits, you should not choose the minimum channel length transistor in anywhere in the op-amp, correct? Because of these 3 reasons that I just explained to you. What is the good channel length? Maybe 3 to 4 times the minimum channel length, correct? Since this is 180 nanometer, I can choose 540 nanometer length as the channel length for my transistors. Correct? So this is the overview that I am giving you just right now. We will solve the problem. Don't worry. I am just trying to tell from where the specs will be coming. So from slew rate, you will be getting, what is the slew rate? Sir has already told you it is nothing but I0 by C. There is no internal compensation capacitor, so it's I0 by CL only. Correct? They have given me the value of CL. Correct? So from slew rate specification, I can get the value of I0. Correct? I know the I0 now. Correct? So from the capital GM, whatever capital GM and R out that I will be getting from the loop gain specification that they have mentioned over here, I know the value of GM1. I can get the value of R0 as well. Now I know what is the current with which the M1 and M2 to bias with. Correct? So from there, I can know what is the W by L because I know the GM, I know the bias transistor. I know the bias current, correct? So from there, I can calculate the W by L of M1 and M2. Correct? Now, once this is done, what about this particular transistor? What about this particular transistor? So remember, whatever current this particular MOSFET, whatever current this particular circuit is consuming, if you consume the same current in your the diode connected load, then the power consumption of the entire circuit becomes 2x. Correct? The power consumption becomes 2x, and that is not a good practice. Correct? So the current that is coming over here, correct? For this example, we will assume that the same current is flowing like this, but when you practically design the circuits, correct, the current that you are dumping into this transistor should be at least 5x or 6x smaller than the current that this entire block is consuming. Correct? Under which case this will not matter if your block itself is consuming a current like 100 or 200 microampere. This is a very small current, right? This is a very small current. Now if you do 5x, if you divide this by 5x, I will hardly be left with 50 to 20 microampere current. This is very, very small value, correct? This is not correct. So now only when your original block itself is consuming such a small current, then you are allowed to consume the same current in this particular device, correct? Because the power dissipation in that case won't matter a lot unless and until you are very much sensitive about the low power designs, correct? Now we understood how to get the W by L ratio of this, how to get the W by L ratios of M1 and M2. What about the W by L ratios of M3 and M4? We have already seen this, correct? If I know the VSD sat of this, I also know the current that is flowing through this transistor is I0 by 2, correct? I can enforce this saturation condition and I can calculate the W by L ratio of this as well. How will you get the width? We know what is the channel length that we are gonna choose. We are gonna choose 540 nanometer for this particular design. Now you have the W by L ratio with you, you have the channel length with you, you can easily get the W dimensions for all these transistors that are present over here, correct? Once all the transistor dimensions are known, the only thing that is now remaining is to select the bias point. Now remember, how will you choose the bias point? The current that is consumed by this M1 is enforced by the current that by the tail current source, correct? Your only job is now is to ensure that your bias is within the input common mode range. What do I mean by that? So if you look, we have solved this numericals, right? We have solved this. There is a range, that there is a bound that I have placed on the V bias. You have to ensure that your input signal, the bias of the input signal along with the peak to peak swing will not exceed these bounds, okay? This is the condition that you have to enforce. And V bias, the DC level, you will generally choose to be around the center of this particular range so that you will have the maximum symmetric input swing that you can give at the input. Is the procedure clear? How are we going to proceed to solve the problem? Any doubts at this particular point? Is the procedure clear at least?
Yes.
Excellent. Okay, so I guess the way we'll solve it, I guess it will become even more clearer. Correct? So now let's start with the loop gain first. So now let's start with the loop gain. Okay, so now what we are going to do is this particular 5-stage OTA, right? The 5-stage OTA, that is the NMOS differential pair with PMOS current mirror active load. We can easily represent it something like this, correct? This is the GM that I have. I have some R0 that is present at the output, and then I have two terminals, correct? I can easily represent it like this, correct? So now what was the diagram that those guys have given to me? So the diagram those guys have given to me was looking something like this, correct? Let me just see, this is R. The V bias will be grounded because I am interested in the loop gain analysis. I have to ground all the static voltages that are present in the circuit. This is R, correct? Then I had a CL over here. This is the V0, correct? And this is where actually I was applying the input, correct? So now this particular block, let me just change the color. Oh no. Yeah. So let me just change the color of the pen. Correct. So this particular block, correct? This is your 5-stage OTA, correct? This block now, I will be replacing with this particular block, correct? Now why I have not taken the output capacitors over here? Because remember, सबका बाप यही बैठा है, ठीक है? This is 10 picofarad. This is very huge capacitor. Whatever femtofarad level capacitance, even if I get around 600 or 800 femtofarad at the output, correct? This 10 picofarad is much larger. So there does not make any sense to consider the parasitic capacitance over here. Correct? The simulator will do its job. Our job is to do a first cut hand calculations and to get the guiding design equations so that if our result does not come accurately in the simulator, we know what parameter to change while doing the design of the circuit. Correct? So now I will be replacing this. So now the circuit will look something like this, okay? Correct? I have minus plus over here. This is the GM. I have R0. Then I have CL over here. Correct? Then I have R. Again I have R over here. This node is grounded. Correct? And remember, they are asking me to do the loop gain analysis, correct? And how we do the loop gain analysis? Can anyone hint me how to do the loop gain analysis of this particular negative feedback system? What do I need to do? Yeah, break the loop. And generally we would like to break the loop at a high impedance node, correct? So I will break at this particular point. So now what we'll be doing is I will be taking this, I will be applying a V test. This is a small signal V test, okay? And then I will be seeing how much voltage is coming back over here, correct? This is the V0 that I have. So this is what I have to do. So now what will be the current that will be flowing at the output over here, correct? So let's say this is I. So now what is the I? I is nothing but minus Gm times V test, correct? Now this particular current will be getting dumped across what? Across whatever load is present over here. Now remember, I have to calculate the net output impedance that is present at this particular node. So there is a R0, there is a CL, but if I look back, correct, I have broken the loop, there is no feedback that is present in the loop now. So now if you trace the loop, there is a R, there is a R again, and this is connected to the ground. So now if I represent the output very roughly, correct, so it is what? R0, 2R is present over here, and there is a CL that is present over here, correct? And across all this load I am dumping this current, correct? So if I want to calculate the output voltage now, so now I have to multiply this I with Z out, correct? So now how to get the Z out? So basically I have I is equal to minus Gm times V test, and Z out I will write it in terms of transconductance. It will become very much easier for me to write it, correct? So R0 I am representing as G0, 2R will be represented as 1 by 2R, plus CL will be represented as SCL, correct? So this is the V0 that I got. Now remember, what is the voltage that is coming back at the input? I have V0 over here, correct? And at this particular node, it is nothing but, so the output voltage I have over here, then I have R, then I have R, correct? This is grounded, and this is where my loop was coming back. This is where I had broken the loop, remember, correct? This is where actually I am applying the V test voltage. So now what is the Vx value that I am getting over here? This is nothing but the resistive division of this V0, correct? This is just V0 by 2, correct? This is just V0 by 2. So let me just write this as equation number 1. By the way, what will be the loop gain now? So the loop gain is nothing but what voltage I am getting, what is the voltage that I am again getting at the point where I had broken the loop. It was V0 by 2. What is the input voltage that I had given? It was V test, correct? So the loop gain of S as a function of frequency is V0 by 2 times of V test, correct? Now from 1, I know what is the relation between V0 and V test, right? So let me highlight this as equation number 2. So now from 1 and 2, what I can write is loop gain of S will be basically nothing but minus Gm by 2 into 1 upon G0 plus 1 by 2R plus SCL. Okay, so this is the loop gain equation with respect to frequency. You can see there is only one pole that is present in the circuit, right? There is only one pole that is present in the circuit. And now remember, this GM I had represent over here. Inside this GM, this is a 5-stage OTA itself, correct? Inside the 5-stage OTA itself, you know that there are mirror poles, right? You remember this particular concept that sir had taught you. Across this diode-connected MOSFET, you had this parasitic capacitance CP, correct? This will cause what? This will cause one pole. This will also cause one zero as well, correct? But as we will see, since this CL is around 10 picofarad, correct? It is around 10 picofarad, and this capacitances that you will be getting, there may be some hundreds of femtofarad, maybe 400-500, maybe they can even max to max reach like 800 femtofarad or 1 picofarad, correct? So what you can see over here is that this will be the dominant pole. There is no way that the pole that is present inside the 5-stage OTA will act as a dominant pole, correct? So that's why I have ignored this pole, but I will highly suggest you that you take this as a homework and follow the same analysis and do the exact analysis. Consider the pole, what is the pole? Basically Gm by Cp, and I guess the zero was exactly lying at the twice the frequency, right? 2 Gm by Cp. The Cp is the parasitic capacitance present at the current mirror load. The Gm is basically the Gm of this particular transistor, the current mirror load. Okay, so I'm not considering them over here. I have ignored it because they will be lying at much higher frequency and they may not affect my circuit that heavily. Correct? That is why I'm ignoring them. If this capacitance would have been around 1 picofarad or 2 picofarad, I had to take this into account because the pole that may be caused by the 5-stage OTA, it may become comparable with what I will be getting over here. Correct? So that is the reason what I have ignored this, and that is the reason why you are getting just one pole system. Correct? Now what is a pole for this particular circuit? So the pole for this particular circuit is nothing but minus of G0 plus 1 by 2R. Just look at the above equation, okay? Minus of G0 plus 1 by 2R upon CL. This is the pole, and what is the DC gain of the circuit? So the DC gain of the circuit will be what? Minus Gm by 2. You just have to put 0 in place of S. 1 by G0 plus 1 by 2R. Correct? So now what we have to do, can anyone please tell me what will be the unity gain bandwidth for this particular loop gain analysis? How can I get the unity gain bandwidth if I know the pole and DC gain?
Just multiply.
Yes, excellent. So now if you just multiply these two, the DC gain and the pole, correct? The unity gain bandwidth will be coming out to be what? Gm by 2 times CL. Unity gain bandwidth for loop. Okay, unity gain bandwidth for the loop, because unity gain bandwidth I can also define for a single pole system without feedback, right? I can just define it for the 5-stage OTA itself, correct? If I don't consider this particular feedback factor, correct? Remember, there is a feedback factor that is present. The feedback factor can be calculated how much portion of the output I have fed back at the input, correct? And that is just nothing but half in this particular case, correct? That is just half. Now if you ignore the factor of half, correct? If you ignore the factor of half, why am I telling you to ignore this? Because I want to see what is the unity gain bandwidth of the open loop system without any feedback in the consideration, correct? Then I have to ignore this factor of half over here, correct? I have to ignore this factor of half over here. So now if I write the UGBW of open loop, correct? Open loop OTA, correct? That half factor will be gone and unity gain bandwidth will be what? It will be increased to Gm by CL. Correct? Remember from the expressions, why did this unity gain bandwidth has increased for the open loop system? You just revise what we had discussed in the earlier classes, right? We first stabilize the system considering that the beta is equal to 1. For the case where we are considering the dominant pole or Miller compensation, in the case of the feed forward compensation, like the story changes, but we are not looking at that particular case over here, correct? Just remember the case and just imagine why, if I reduce the beta from beta is equal to 1 to beta is equal to half, why my UGBW is actually reducing by the factor 2 over here, correct? Just recall that, because if you change the A beta, correct, what you are essentially doing is you are shifting the entire curve down, correct? You are shifting the entire curve down, so the point where it will intersect the x-axis, it will also change. That is why I have written that for the open loop, since the beta is equal to 1, I am not considering any feedback, my unity gain bandwidth should be doubled compared to the case when I am considering the unity gain bandwidth of the loop with beta equal to 1 by 2. Is this point clear to everyone? Is this point clear to everyone? Why UGBW has got multiplied by the factor of 2 for the case of open loop OTA?
Yes.
Okay. Okay, so now we have got the UGBW and now we have also got this. So now what will be the Bode plot diagram that will look for this particular case? By the way, what is the time? I guess I will have to take few more minutes, maybe 15 or 20 minutes more. If some of you wants to leave, it's completely okay, but I want to make sure that I will give my best attempt to solve this problem, because I don't want you guys to just get the theoretical stuff and leave this course. I want you to become good circuit designers, okay? Now I have a flat gain till the pole and then I have a 20 dB per decade roll off, correct? And then this axis is what? Omega. On the y I have loop gain of j omega and mod of that. On the downwards y-axis, I have what? Angle of loop gain of j omega. Correct? So till this particular point, the moment I hit the pole, how much phase shift will I incur if I start from the 0?
45 degrees.
Yes, very good. So this is minus 45 and this is going to minus 90 because it's a single pole system. Okay. By the way, after this UGBW, right, maybe after 4x or 5x difference, you will find that your another pole will also hit, and so this will be minus 40 dB per decade roll off. This is minus 20 dB per decade roll off, and again at the 2x frequency you have a 0 that will be getting contributed because of the mirror current mirror load that is present, correct? So this minus 40 dB per decade roll off, again slow, it will become slower to minus 20 dB per decade. But this will not matter because it is happening at a much higher frequency with respect to UGBW. So the phase degradation that will cause by this pole at this particular UGBW, correct, I can ignore it if there is a, if this pole, the parasitic pole 2, let's say it is at least 10 times of omega UGB, correct? If it is, let's say, 5 or 4 times of omega UGB, then what you need to do, your phase margin will degrade now, correct? This pole will have some contribution, correct? But remember, how much margin do I have over here? This is minus 90 degree, correct? I am still 90 degree away, correct? My phase margin is 90 degree because I am still 90 degree away from 180. So even if this pole contributes 15 or 20 degree, correct, then this will be what? Then I still have the, if 15 degree degradation is there because of the parasitic pole, then at least I have around 75 degree of phase margin with me, correct? You guys have to ensure, you guys have to calculate what at what frequency this pole will be coming. I will be giving you all the necessary tools and equations. You guys just check, and if I have made any mistake means in the values, just correct by yourself and just see if this pole really affects at this particular frequency or not. Correct? We have also drawn this pole zero diagram. So now the question that they are asking is, okay, we have found out the open loop, but just look at this question. They are also asking us to find out the closed loop gain and the 3 dB bandwidth of the closed loop system. The pole that you are seeing over here, it is nothing but omega 3 dB of the open loop system. Correct? Now we are doing the closed loop analysis now. Correct? Closed loop analysis. Now a very quick refresher. If I have a system which I can represent with something like this, correct? And if I put it in the feedback factor beta, correct, this is plus, this is minus, and now if I try to find the transfer function of this system, so it is V of by V in of S, correct? If I do it, then what it will be? So it is A naught upon 1 plus S by omega P, basically the open loop transfer function upon 1 plus A beta, right? A is what? A naught by 1 plus S by omega P into beta, correct? So now what you can see over here, so if I just multiply both the stuff by this particular factor, then what will I get? A naught by A naught beta plus 1 plus S by omega P, correct? Now if you look at the pole of this system, the omega 3 dB is what? Omega P times 1 plus A naught beta, correct? So can I say that for a single pole, approximately a single pole system whose second or third pole may be lying at a far away from the omega UGB, can I say that the 3 dB frequency of this closed loop system with the feedback factor beta is nothing but the 3 dB frequency of the open loop system multiplied by the 1 plus A naught beta, right? This is what I can make, and we have also seen this when we were doing the stability analysis, correct? So I'll be using the same formula now, right? Omega 3 dB will be nothing but omega P, correct? Now what is the omega P? Omega P is our Gm by 2 into 1 by G naught plus 1 by 2R, correct? Plus 1. By the way, what is this? Let me just see. I guess I'm making some mistake. the pole was at this particular frequency, correct? So what I am writing over here is not a pole, it is a factor 1 plus a beta actually, correct? So this 1 plus a naught beta is factor what I am writing over here, correct? And now I will be multiplying it with omega p. What is the omega p? So the omega p was nothing but g naught plus 1 by 2r by cl, correct? So this is what I had got. So now if I just expand this a little bit, omega 3 dB of closed loop system is what gm by 2cl, correct? Why 2cl? Because remember, this is g naught plus 1 by 2r, this is also g naught plus 1 by 2r. This will get cancelled out when I multiply it, right? And this is what I will be having, g naught plus 1 by 2r by cl, correct? So this is a formula that I got for the omega 3 dB of the closed loop system. But remember, now I have to compare these two terms, okay? I want to see which of these terms is dominating. So remember the spec that those guys had given. They want me to have a minimum loop gain of 40 dB, which means 100 volts per volts, correct? Now let's try to do that, correct? Let's try to do that. So what was the loop gain that I had got? So the loop gain that I had got was nothing but minus gm by 2 times 1 by g naught plus 1 by 2r. I am talking about the DC loop gain, correct? I am talking about the DC loop gain, correct? So now this thing that they are mentioning is to have the this has to be greater than or equal to 40 dB, correct? Now if you look at this condition, then what you will be getting is gm by 2 is at least 100 times g naught plus 1 by 2r, correct? Now remember this condition, okay? Remember this condition, and now let's look at the closed loop 3 dB frequency that I got, correct? Are you able to identify this gm by 2 over here and g naught plus 1 by 2r over here, correct? So what I am trying to say over here, the gm by 2cl term is at least 100 times greater than this particular quantity. So what I can write is omega 3 dB cl is approximately equal to gm by 2cl. Okay, this is the 3 dB frequency of the closed loop system, correct? Now can anyone comment on the unity gain bandwidth? Can anyone comment on the unity gain bandwidth of the open loop system and the closed loop system? So for example, if I have a transfer function a of s, correct? This is the open loop case, and I got one open let's say omega UGB under the case of open loop, and then I put it in the feedback, correct? And then I got omega UGB, just a minute, omega UGB of closed loop system. For a single pole transfer function, what happens to the unity gain bandwidth of the closed loop system with respect to open loop system? Does it changes, increases or decreases?
Decreases.
Decreases, okay. Can you, okay, so how did you say that? Can you explain it?
3 dB will be almost same. 3 dB bandwidth.
Yes, it will be exactly same, correct? Why is it happening? I will just show you diagrammatically. Remember, what does the feedback do? Can anyone tell me what does the feedback do to the bandwidth of the system? I am talking about the 3 dB bandwidth of the system. What does it do?
Okay, bandwidth of the system will reduce, but 3 dB will remain same.
3 dB will remain same. And now talking about the bandwidth, right? Remember the DC gain will be reduced, right? DC gain will be reduced, but your 3 dB bandwidth has increased now, correct? This is what I am talking about. This is omega 3 dB of closed loop system. This is the, what is this point? So this is omega 3 dB of open loop system. But remember this point, the closed loop, the unity gain point is remaining exactly same, correct? So your omega UGB, let me just write it, omega UGB of closed loop system will be exactly same. We have already calculated it, right? It was gm by cl. It came out to be gm by cl. The 3 dB frequency came out to be gm by 2cl, correct? And now if you ask why it is only a factor of 2, remember the gain will not, the gain is lower over here, correct? The after doing this, putting this in the closed loop system, the gain has reduced now, correct? So that is why you are seeing that this factor that you are seeing over here, this will be very, very small, correct? Because it is just 2, there is only a factor of 2 difference between this particular point, correct? So now I hope this is clear. Now once this particular thing is done, any doubts at this particular point, I will be happy to answer. Okay, great. So if no doubts, then let's try to calculate the GM of the circuit, because we are still not yet at the point where we have calculated GM and R out of the circuit. Unless until I calculate GM and R out, I cannot get a specifications to do the transistor level design. Okay. So now what is the conditions that they have given me? First, let's look at the 3 dB frequency. F 3 dB of the closed loop is greater than or equal to 100 megahertz, right? And what is the 3 dB closed loop frequency that I was able to find? So this is the omega 3 dB closed loop, right? GM by 2CL. So F 3 dB will be nothing but GM upon 2 pi times 2CL, right? This has to be greater than or equal to 100 into 10 to the power 6. Correct? The CL capacitor was given to me, remember, 10 picofarad, right? So GM has to be greater than or equal to 2 into 3.14 into 2 into 10 picofarad, correct, into 100 into 10 to the power 6. Now if you do this calculation, right, the GM will come out to be greater than or equal to 12.56 millisiemens. Correct? At least I got a spec on the GM of the transistor. That's a very good news. Correct? So now remember this condition also. From this condition, now if I know the value of GM, correct, they have given me the value of R. Remember this R that is placed in the feedback, right? The feedback transistors, the feedback loop transistor. So their values have been given in the numerical. Remember, these have been given at around 50 kilo ohms. Correct? They have given it to me. So now if I know that this resistance value it is 50 kilo ohm, I know the value of GM. I can easily find out the condition on G0 from here. Right? So if this is A and this is B, correct? So I will write over here from A and B. From A and B, correct? What I know is GM by 200 is greater than or equal to G0 plus 1 by 2R. Correct? So from here I will get a spec on G0, that G0 should be less than or equal to GM by 200 minus 1 by 2R. Okay? So from here G0 should be lesser than or equal to, GM was what? 12.56 millisiemens. Here I have a factor of 200 minus 1 by 2 into what is the resistance value they have given? 50 kilo ohms. Okay, so the G0 will be coming out to be less than or equal to, let me just see what is the value. The G0 will be coming out to be around 5.28 into 10 to the power minus 5, right? So the R0, correct, the equivalent output resistance will be coming out to be greater than or equal to 18.939 kilo ohms. Okay, so I also got a spec on the R out now. Correct. So the specs that I wanted on GM and R out, I already got that. So that's a very good news. Now one problem is I could have directly used this R0 value, right? So for example, if you look at the output impedance now of your 5-stage OTA, correct? Now forget about the feedback, because they wanted me to design the non-inverting amplifier from the specs that they have given on the closed loop system. I was able to calculate the spec on the open loop system. From the specs on the open loop system, I was able to get the GM and R0 that I need from my amplifier, correct? And from here, I got the spec on the output impedance of the 5-stage OTA. What was the output impedance of the 5-stage OTA? It was nothing but R0 of NMOS parallel of R0 of PMOS, correct? Now this is what, if I assume both of them are same, this is R0 P by 2, correct? Now remember R0 was nothing but 1 upon lambda ID. Correct? R0 was nothing but 1 upon lambda ID. And what was ID? ID was nothing but I0 by 2. Correct? ID was nothing but I0 by 2. So now this factor will be what? 1 upon, this will be just reduced to lambda times I0. Correct? So now if the lambda would have been given to me in the PDK that the professor has provided, from this R0 value, I could have easily got the spec on the I0. Correct? I would have easily got the spec on the I0, but unfortunately, since this PDK was, I guess, handmade, or I don't know what they have done over here, but you will not be seeing, at least I was not able to find the parameter lambda. Correct? The lambda factor is missing in this particular PDK. Normally it should be given. What should be the value of lambda generally? Correct? Since the lambda is not given over here, you can either do one thing. You can either assume this value yourself to be something like maybe 0.05 or 0.03, something like this. You can assume it and then calculate the I naught from here. Correct? But since the I naught has not been given over here, what I will be doing is I will be going with the different method and I will be using the spec on the slew rate. Okay, remember, whenever you know the lambda, always calculate the ID from here. Okay, that will be always the best case. But if this is not given, I can go with the secondary specs of the op-amp, that is the slew rate. Correct? So slew rate I will be assuming to be something like 100 volts per microseconds. I have already discussed this. This is what? This is I naught by CL. Correct? So from here, what I can get is I naught is nothing but 100 into 10 to the power 6 into CL. Correct? CL is 10 picofarad. 100 into 10 to the power 6 into 10 into 10 to the power minus 12. So the spec that you will be getting on I naught is just 1 milliampere. Excellent. I got a spec on the I naught. I know what is the bias current through each transistor. I know the GMs of the input differential pair at least. Correct? So now what is my job? My job is to calculate the W by L ratios now. So now let's move on with this particular section. Calculation of W by L. And remember, even though we have ignored the parasitics inside this particular transistor, if the output capacitance was smaller, you would have been forced to include the poles and zeros that were present at the 5-stage OTA, within the 5-stage OTA itself. Now to make your life hell, correct? Now to make your life hell, remember what these parameters are. You guys remember when we talked about the capacitances in the MOSFET? I had discussed about the junction capacitance, the side wall capacitance. You guys remember this or you have forgotten that?
Yes.
You remember this, right? Yes. And along with that, I had also told you that the CdB varies something like CdB naught upon something was there, 1 plus some potential, some constant potential was there, or built-in potential was there, and some bias voltage across the CdB was there over here. And it was varying with the factor M. And that M also we have seen. This is the same M that you are seeing in the PDK. Correct? Now, if the professor wanted to make your life hell, correct, he would have asked you to calculate these CdB from these MJ, MJSW, CJ, CJSW. Correct? Then you have to take into account all the way we have calculated the capacitance, right? The side wall capacitance, the perimeter we had taken into account, the junction depth of the source and drain regions we have taken into account. Correct? All those parameters you would have to take into account. Then from there on, you have to calculate the CdB naught. From CdB naught, you have to calculate the CdB by knowing this M and the built-in potential, which may you have to calculate by yourself only by using the formula KT by Q ln of what? NA by Ni square. Correct? From there on, you will get the value of CdB. Similarly, you have to do it for CSB. Correct? Once CdB is known, once CSB is known, the other parasitic capacitances remaining are what? CGS and CGD. Correct? CGS and CGD are easy to calculate because as we know, since MOSFET is in the saturation, this is nothing but 2 by 3 omega L Cox, and CGD is nothing plus some overlap capacitance. I had forgotten that. C overlap into omega L, and CGD is nothing but C overlap into omega L only. Correct? So now, if we had asked you to calculate this by yourself, this would have become a very lengthy numerical, right? Because you are literally going into the structure of the MOSFET. From there on, you got the CdB naught. From there, you got the CdB. From here, you got the CSB as well. You had to calculate the built-in potential by yourself only. Correct? By given dopant concentration. Then you have to calculate CGS, CGD. And then once you know this, correct? Once you know this, then remember what was the parasitic capacitance at the current mirror load that sir had given, correct? It was looking something like 2 times CGS, correct? Plus 2 times CdB, something like this. I don't remember exactly, but you can easily figure this out, correct? Then you should substitute these values over here. After that, you will get the value of parasitic capacitance inside the OTA. And once you know this value of CP, after that, you can calculate the values of poles and zeros that are actually getting contributed by the 5-stage OTA. So just see how complex this numerical I can make depending on what values I am giving to you, correct? I can make this as a complete final year project of the BTech guys and then giving this PDK, and then I can ask them to design the two-stage OTA. I can ask them to put it inside a non-inverting amplifier. I can also ask them to make a filter out of this OTA, correct? The active RC filters that we had seen. So just try to link everything, whatever we have studied till now, everything is coming into the picture, from the semiconductor device physics up to whatever formulas, up to whatever current mirrors, the differential pair, whatever we are studying, all of this is coming into picture only in this one numerical. Okay, this is the importance of this numerical, and that is why I have to solve it in front of you, so that you should not face any design issues after solving this numerical now, correct? You can directly go to the Razavi and maybe some other books and try to solve the single stage op-amp numericals after this. Okay, so now let's try to calculate the W by L ratios now. So from the PDK, I am taking some data now. Mu n is around 273 centimeter square per volt second. Mu p is around 115.7 centimeter square per volt second. Correct? The thickness of the upside was given as 4.1 nanometer. Correct? The epsilon of SiO2 they have given around 3.97. Correct? So first let's calculate the COX, right? Because we need the COX in the current equation. So COX is what? Basically it is nothing but epsilon R into epsilon SiO2 divided by TOX. Correct? So this will be what? 3.97 into 8.85 into 10 to the power minus 14 divided by thickness of oxide is what? 4.1 nanometer. 4.1 into 10 to the power minus 9. Correct? So the COX will be coming as 8.57 into 10 to the power minus 3 farad per meter square. Now you have to be absolutely careful while multiplying the mu n and COX, because remember the units, this is centimeter square and I have calculated the value in meter square. So do not get confused, be very sure with the units of the mu p COX and the mu n COX, okay? So now if you multiply them, I'm just writing the values directly. Okay, the mu n COX value will be coming out to be around 235 into 10 to the power minus 6 amperes per volt square, and mu p COX, this will come out to be something like 99 into 10 to the power minus 6 by volt square. Correct? So these are the values that we are going to use. Correct? So these are the values that I am going to use now. So now let's move on to the transistor level design. Transistor level design. So now what we have to do is, basically we know that the current flowing through the transistor 1, 2, 3, 4. So what does the transistor 1, 2, 3, 4 mean? So if I show you the diagram of the 5-stage OTA, right? Yeah. So remember the M1, M2 are the differential pairs. M3 and M4 are the current mirror load that you have, and your M5 is nothing but your bottom transistor that you have over here. Correct? Just remember this. So now once you know this, now this is nothing but it is biased at I0 by 2. Correct? So these are biased at 0.5 milliamperes. Correct? So now once this thing is clear, now one more thing is we have to see how can we apply the equation. So now how can I calculate the value of GM first? So first GM is basically, no, I don't have to calculate the value of GM. From GM I will calculate the W by L, right? So this is 2 mu n COX W by L times ID. Correct? I know the value of GM over here, correct? And then I know the value of ID over here. I know the value of mu n COX. I can easily calculate the W by L. I am doing this for transistors M1 and M2. Okay, because these are identical. So now if I just square on both the sides and substitute the values, square is 2 times mu n COX is what? 235 into 10 to the power minus 6 into W by L of 1, 2 into ID. ID is what? 0.5 into 10 to the power minus 3. So now if you solve this, W by L of 1, 2, this will be coming out to be around 671.29. And remember, we have already talked about how to choose the channel length, right? We are going to choose the channel length around 540 nanometers, so you can easily calculate the value of W from here. Now once I know this, I would like to calculate the VGS minus VTH of this transistor as well, correct? So now I know GM is nothing but 2ID upon VGS minus VTH, correct? So VGS minus VTH is 2 times ID by GM, correct? Now if I move up over here, so VGS minus VTH will be nothing but 12.56 into 10 to the power minus no, this is not correct. 2 into 0.5 into 10 to the power minus 3 divided by 12.56 into 10 to the power minus 3. So VGS minus VTH, that is the overdrive of the transistor 1, 2. If you calculate, this will be coming out to be very small value, around 79.61 millivolt. And remember, if any value comes out to be this small, always remember that this is the minimum VD side that you need to maintain, correct? Now while doing the practical design, what you will do is you will add some margin on top of it, maybe 30-40 millivolts, correct? And then you will assign the VD sat. So if this is 80 millivolt, then ideally you should assign the VD sat of 120 millivolt, correct? So some headroom will be there, and across the PVT variation, even if there is a threshold voltage variation of 30-40 millivolt, the your transistor will still remain in the saturation, correct? I am not doing it over here, but always remember, while doing the practical design, you have to keep this margin, especially you are gonna do the tape out of your circuit and you are gonna fabricate your circuit, correct? You have to make sure, or else when the chip comes back, you will keep on crying that my MOSFET entered into the triode region, right? You don't want that to happen with you, correct? So now once this is done, we got the size of the input differential pair. Now let's go on with the sizes of the current mirror load, correct? By the way, if you guys have any doubt, please feel free to poke me. Transistor level design of current mirror load. Okay. Now, how are we going to do this? Remember, if the specs on the ICMR are not given, then we have to choose some specs, right? ICMR minus is 0.8 volts. ICMR plus is what? Around 1.6 volts. By the way, this is just a quick mic test. Are you guys able to hear me or no?
Yes.
Okay, great. Yeah. So now, ICMR minus. So we have already saw the upper and lower bounds, right? We have already know what is ICMR minus and ICMR plus. So I am just borrowing the equations from there, what we have seen in the first 1 hour of this class, right? This is VD sat of M5, that is the tail current source, correct? Then you have VD sat of first transistor plus threshold voltage of first transistor. On the other hand, ICMR plus is basically VDD minus VT3, correct? Mod VT3 plus VT1, not mod VT1, only VT1 because it's of NMOS, and then you have mod VSD sat of transistor 3, correct? Now just look at the equation number 1, okay? I know the value of VD sat, correct? This the 79 millivolt value I got. This is the same thing over here. By the way, threshold voltages, I guess I forgot to mention, threshold voltage values had been given. Let me just quickly check what were the values and get back to you. Just give me 1 minute. We have to go to the PDK and then we have to check it. I don't want to spend a lot of time. The threshold voltage value was given around 370 millivolts for VT1. It was given around 370 millivolts. And now let me just check about other thing. Yeah, this is clear. Okay, this is okay. And now this VT1, the VT3 value is also very close. You can easily approximate it as around 370 millivolts. At least this is what I am doing. If you find from the PDK that these two values are different, please take them different. Usually they will not be same. There might be some 40 to 50 millivolt of difference may be there, correct? I am just taking them to be same over here just to simplify my life. But while doing the design, just note of this fact that some difference of 40-50 millivolt will exist over here. Okay, so now if I know the VD sat, if I know the VT1, if I know this is 0.8, I can easily calculate the VD sat of M5, correct? So let me highlight this as equation number 1. Let me highlight this as equation number 2. So from 1, I know that 0.8 is equal to VD sat of M5 plus VD sat of M1 was what? 79.61 millivolt, correct? Plus 370 millivolts. correct? So VD sat of M5, you are getting around 350.39 millivolt. So this is the VD sat that I got. And remember, this transistor is biased at a current of I0, correct? Not at I0 by 2, correct? Similarly, from 2, what I can write is 1.6 is nothing but 1.8 minus VD sat of 3, correct? That is VSD sat of 3, not VD sat of 3. So basically, what you will be getting from here is VD sat of 3. Basically, this is the saturation overdrive voltage of that particular PMOS. The bottom notation may be little bit incorrect, so just adjust with this. This is 200 millivolt, correct? So now we got for the transistor M5, that is the tail current source. This is for the tail current source, and this is for the current mirror load. This is for the current mirror load. We know the currents flowing through both of them. We know the VD sat overdrive of both of them. Now it's time to use the current equation and to calculate the W bar sizes of them, correct? So let's start with this particular thing, right? So now let me highlight this as maybe 3. Let's say this is, I am highlighting as 4, correct? So from 4, the current through transistor 3,4, correct, is nothing but half mu p Cox W by L of 3,4 into VSG minus mod VTP, that is the VD sat that we had calculated, the whole square, correct? So the current from 3 to 4 is basically 0.5 milliampere. This is half. What is mu p Cox? 99 into 10 to the power minus 6 into W by L ratio we have to calculate. And what is the overdrive we got? 200 millivolts, right? So if you just calculate this, then the W by L ratio of 3,4, this will come out to be around, this will come out to be around 252.52. Correct? We got the W by L ratio of another 2 transistors. Similarly, I will write from 3. Correct? So again, I am writing the current equation for the tail current source. Okay? Tail current source. So this is half mu n Cox W by L of the tail current source into VD sat of the tail current source, right? So I know this value. This is 10 to the power minus 3. 1 milliampere current flows through the tail current source. This is half. Mu n Cox is 235 into 10 to the power minus 6. This is W by L ratio of M5 that I have to find into VD sat of M5. This is 0.3539 the whole square, correct? So the W by L ratio of the phi that you will be able to find, it will be close to around 67.95. Correct? Now nothing is left in the circuit. Correct? Literally nothing is left in the circuit. We have calculated the W by L ratios of all the transistors 1, 2, 3, 4 as well as the phi. Correct? The only thing that you may ask, that you may doubt that one thing is remaining is to calculate the W by L ratio of this current mirror transistor, right? That is giving the bias voltage to the bottom tail current source, correct? So now you can size this as the same size of this particular thing, or you may decide to size it maybe 5x smaller, correct? 5x or 6x smaller, correct? 5x or 6x smaller. Now you can decide it by yourself what you need to do. If you have some specifications on noise as well, then this may play an important role, correct? Now one more thing that I just wanted to see is if anything is remaining that I wanted to discuss. Let me just see. Yeah, we have one more thing that is remaining is, if you don't want to do all that Gadha Majduri, right? So Gadha Majduri of what? I told you about all that CJ, CJSW, CDB and all, correct? So I had told you about that is a very lengthy procedure, correct? You may not want to do it every time. That is gonna cost a lot of time, correct? So now one hack I would like to tell you that came from the experience is basically, if you are designing the circuits in minimum channel length, this will not directly apply if your transistor is having, let's say, 540 nanometer channel length or something. But if you are designing RF circuits or circuits which is having the channel length that is the minimum channel length of that particular PDK, right, then you can note down these values. This will come from experience and by looking at the cadence tool extensively for many years. Okay, so the CGS value, right, that you will be getting, if you normalize it with respect to the width of the gate, correct, So this particular density number, for maybe even if you are designing the circuit at, let's say, 180 nanometer or at 45 nanometer, it does not matter. It does not matter. This particular density of the capacitance per unit gate width, it will remain approximately constant to 1 femtofarad per micrometer. Similarly, if you calculate for CGD per unit gate width, this will come out to be around 0.5 femtofarad per micrometer, and your CDB or CSB per unit gate width, this will come out to be around 1.5 femtofarad per micrometer. Now note, this is only valid for minimum channel length transistor. Okay, minimum channel length transistor. Now if you increase your L, if you scale your L, if you increase your L by 3x, you definitely know what happens to CGS and CGD. Correct? They directly scale up, they directly scale with WL. Correct? They directly scale with the W into L. But what about the CDB and CSB? It is not so easy, because remember the CDB and CSB formulas that we had seen in the perimeter and all, correct? Whatever perimeter we had seen, the L did not came into the picture. Correct? The channel length did not came into the picture. If you have forgotten, then just go back to, I guess, 2 or 3 classes back and see the lecture or lecture notes. You will see the expression for the CDB and CSB that I had written. But if you are designing, if you want some rough calculations, at least some numbers for the hand calculation, this is a pretty good approximation that you can use for the minimum channel length transistor. If the channel length is not minimum channel length, if you have increased it by 3x or 4x, then scale your CGS and CGD by the same factor. CDB and CSB, you don't need to do anything. Approximately it will remain same, or it may also increase, but that effect you directly cannot predict directly. Okay, so that value you can consider approximately same. So now these are good enough for first hand calculations of finding out the poles and zeros, so that you don't have to do a lot of lengthy calculations, and then from here calculate the poles and zeros and see how much your phase margin is getting degraded. Because remember, even though your poles are lying outside the omega UGB, how much distance away they are from the omega UGB, it will matter, because your phase margin actually depends on that particular factor. The separation between the parasitic second pole that is there in the OTA and the UGB, the distance between both of them. Ideally, if you make it 10x separation between the omega UGB and omega pole of OTA, correct, that is gonna be good, because at 10x frequency the contribution will be almost negligible. Okay, so now you can proceed with these values, the density values that I have given, assuming some channel length of 540 nanometer, and can calculate the parasitic capacitances that are present in the OTA, calculate the zero, calculate the pole that you are getting, compare omega P and omega Z that you got with respect to omega UGB, and see how much phase margin is actually getting degraded from this. Correct? Now once this is completely known, our complete numerical is done now. If you really want to go and design this in the LT Spice, you are free to do that. The other questions that these guys had asked is, they are also asking the closed loop transient response. They are also given the amplitude of the sinusoid that you have to give. Correct? Remember, they have, in some cases they are giving the frequency of the input sinusoid exactly equal to 3 dB frequency. Sometimes they are giving the frequency which is 10 times smaller than the 3 dB frequency. Correct? So the circuit will react little bit differently to both these frequencies. Correct? So you can see these effects directly in the simulator, or you can also get some intuition based on whatever we have discussed till now. They were also asking us to tabulate the GM, GDS, CGS, CGD and VOV of all the transistor. I have already told you how to calculate CGS, CGD. We have also seen how to get the overdrive, that is the overdrive voltage, the VD-SAT voltage of all the transistor. So now I have solved almost 60 to 70% of this numerical. Just get these values, go to your circuit simulator, run the simulation and see what is the response that you are getting. I guess this can become a very good project now, and maybe you can definitely mention it on your resume if you have done such a detailed analysis. Okay, so I will be stopping over here. I have done whatever I have wanted to cover for this particular lecture. If you guys have any doubts, please feel free to poke me now. This is a good time to ask. Any doubts in this example? Is it clear?
Yes, it is clear.
Okay, excellent. Uh, Other guys, any doubts from whatever we have covered till now? I know I already extended like 40 minutes, but as I mentioned, I don't want you to just get theoretical knowledge out of this course. I want you to have that design experience so that you can go and design these circuits yourself. You should not have that guilt that even after studying the circuits course, I'm not able to design the circuits. This example is a testimony now that once you have designed this, you have understood this clearly, it should not be difficult to you to design any other op-amp related circuit now. Correct? Any doubts at this particular point, guys? This will be a last call for doubts. I have to go to mess or else I have to remain hungry for till tomorrow morning.
No.
No? Excellent. You enjoyed or it was completely above your head, the example?
No, I couldn't get it.
You got now or it went above your head?
No, I got it.
Oh, you got it. No, okay, great. Excellent. Okay, guys, then I guess we will close the session over here. Thanks again for staying here for around 3 hours. Have a great evening ahead. Have a great weekend ahead. Take care. Bye-bye.
Thank you. Bye.
Bye.